We have looked up to the stars and galaxies in awe and wonder for millennia, trying to understand our place in the universe. Current technology is enabling us to see further and farther back in time with much more detail than ever. The next generation of orbiting telescopes is soon to enter service. Who knows what giant leap they will make in our understanding of the universe. Since its launch in 2013, ESA's Gaia observatory has been constantly mapping our galaxy, creating the most accurate and complete multi-dimensional map of the Milky Way. This latest observational dataset has been released and contains even more and improved information about almost 2 billion stars, solar system objects and extragalactic sources. Our Sun travels at 240 kilometers per second around the galactic center and will take 220 million years to complete one orbit. The Gaia dataset includes stellar positions, stars' distances, and motions across the sky, plus color information, and most significantly, the radial velocities for 33 million stars within the Milky Way. This allows astronomers to create the most accurate and complete multi-dimensional map of our astronomical neighborhood. Another novelty in this dataset is the largest catalogue yet of binary stars in the Milky Way, which is crucial to understand stellar evolution. At the Observatoire de Paris in Meudon, Paris, France, scientists form part of the Data Processing and Analysis Consortium, some 400 scientists from 20 countries who are responsible for the processing of Gaia's data with the final objective of producing the Gaia catalogue.
So Gaia is extremely important for all fields of astronomy. The Gaia catalogues, that results contain a huge amount of information that will provide the material for the work of astronomers in around the world and for many, many years.
With each new release, the observed stars, solar system objects and extragalactic objects increase, and many more details are added to what is already the most detailed overview of our galaxy.
So Gaia is incredible satellite which looks at the stars, which measure 1.8 billion stars, but obviously it goes from what is nearby, asteroids, up to very distant quasars. For these 1.8 billion stars, it's able to find their distance, their astrophysical parameters, their ID card in some sense. Up to now, Gaia had given already a lot of information about stars, but now it's going from astrometry, the position, motion of the stars, up to astrophysics, knowing the characteristics, the astrophysical parameters for nearly 500 million stars. It is able also to find a lot of variable stars, to classify them. It's able, of course, also to see what is variable in terms of position, and so it helps to find binary stars which move on the sky or on the spectrograph.
And this time we provide new measurements such as star brightness in the RVS spectral range, rotational velocities, atmospheric parameters, chemical composition, and the RVS spectra also provide information on the abundance of the interstellar material that is present between stars.
So Gaia is observing with astrometric instrument which measure the position of the objects, and from this position it gets the motion of the object with time on the sky. That's astrometry. Then Gaia measure also the light of the object, measure spectrophotometry for the object, and from this it can infer the color of the object, but also you can derive from that all the astrophysical parameters that you can get, like temperature, effective temperature, gravity, and so on. You can also infer what is the extension of light in the distance where it comes from the star to us. So the third instrument now is a spectrograph, which is able to see the spectrum of the star. And so when you see the lines of the spectra, you see at which speed the object is going towards us or and the other way around. Or when it's moving periodically, then you can detect through the motion of this radial velocity. That's the three main instruments of Gaia.
Even older than Gaia is the venerable Hubble Space Telescope. It too continues to contribute to the science of cosmology.
To my mind, the most important discovery from Hubble is the discovery of dark energy. There have been a lot of interesting discoveries, certainly. Certainly the fact that there are billions and billions of galaxies that we had no idea there were that many. The work that we were doing on exoplanets with Hubble has been interesting. I mean, Hubble has carried such a wide variety of results that it's hard to pick a single one, but I do feel the dark energy is the outstanding discovery. And what that means is simply that space, we always thought that space would contract because gravity would pull it together. We knew it was expanding, but we thought the expansion would slow down. Well, instead, the expansion's speeding up. And that is a very exciting thing to me.
Because the Hubble Space Telescope is operating so well and is so scientifically effective right now, scientists are using Hubble to investigate some of the deepest mysteries of the universe. One mystery is dark energy. That's the name just kind of plastered on this phenomenon that Hubble and other telescopes together, we found that the universe expansion has been accelerating for the last few billion years. Well, what is causing that? We don't know. It's something about a repulsive force that we may not fully understand, or new physics that we don't fully understand. But Hubble was used along in complement with some telescopes on the ground to determine that the expansion of the universe is in fact accelerating by something we're now calling dark energy. And without Hubble, we would have not been able to make this detection, which is now a Nobel Prize winning discovery.
This explains why the universe appears to be accelerating now when it used to be slowing down because of gravity. So now the question is, well, is this a simple story or is it complicated? Is there more than one kind of dark energy? Has the dark energy itself changed over time?
So Hubble is now being used to refine even further that expansion rate of the universe in our current epoch, and trying to compare that to what might be predicted from looking at other measurements of the universe with other telescopes. Right now we're finding a discrepancy between what we might have expected and what we're actually measuring. So that's one realm where Hubble is really at the cutting edge of helping us understand, or at least open up, new mysteries of the universe.
Astronomers are still puzzling over dark matter and how it behaves. They have found small, dense concentrations of dark matter that bend and magnify light much more strongly than expected. Dark matter makes up the bulk of a galaxy. The gravitational influence of dark matter is thought to tie the galaxies together in massive clusters. There is so much regular matter and dark matter concentrated in these clusters that their gravity magnifies and warps light from distant background objects. By studying how the light distorts the background galaxies, though, this gravitational lensing can help map where the dark matter is in galaxy clusters. Images of lensing galaxy clusters are filled with the smeared images of remote background galaxies. The higher the concentration of dark matter, the more dramatic its light-bending power is. Smaller clumps of dark matter associated with individual galaxies in the galaxy cluster create more distortions. In some sense, the galaxy cluster acts as a large lens that has many smaller lenses embedded inside. But strangely, astronomers found that 3 galaxy clusters used in their study had concentrations of dark matter that are so massive that the lensing effects they produce are 10 times stronger than originally expected. Soon to be launched, ESA's Euclid mission aims to investigate this dark matter, dark energy, and the expanding universe in even greater detail. Euclid will image billions of galaxies with unprecedented accuracy out to a distance of 10 billion light-years. These measurements will enable astronomers to improve their understanding of the expansion of the universe and the growth rate of cosmic structures.
Euclid is a cosmology mission. It will study and try to better understand the geometry and the nature of the dark matter and dark energy, which is the peculiarity of Euclid. It's a telescope that will scan the sky with an accuracy that is unprecedented. So this is really something that no other spacecraft did before. This will allow to get additional information and to better understand the story and for the expansion of the universe and the growth on the cosmic structure.
Euclid carries a 3-mirror and astigmat design. The primary mirror is 1.2 meters in diameter. This type of design allows for a greater field of view, covering the visible wavelengths and simultaneously near-infrared spectroscopy and photometry.
It was a very important milestone because it's somehow the starting point of a new phase of the project, because so far the 2 parts that you can see, the upper part that is the payload module and the lower part that is the service module, have been developed and tested separately. So today with the mating we start a following phase, the next phase, with both the 2 main constituents of the Euclid spacecraft are together.
Indeed, this is a completely new design with a lot of challenges involved with this mission. And we have put together a team of about 120 companies in Europe, which are working together in good synergy for several years. And we are very proud of the results achieved today.
The mission is designed for a 6-year lifespan. However, an extension of a further 5 years is contemplated, dependent on the spacecraft's onboard resources.
With the mating today of the telescope with the service module, we achieve a major milestone in the integration of the flight satellite. It has been a long journey because the 2 elements have been developed independently for several years, and now for the first time they are mated together, and this makes us very proud of the achievement.
So the telescope was already delivered here in October last year and was put in the clean room on the fixture, ready to be mated. In the meantime, we finished the work to be done on the remaining part of the satellite, which is here. And today we released the telescope from that foundation, and we move it to the SVM by crane. It is a very dedicated operation because the tolerances or the budget we have for the mechanical stresses is very small. So it's a very fragile telescope because it needs to be light. So it's quite fragile. So for this operation, there was a tight allocation for the stresses. And the stresses they measured at every step on the feet which support the satellite on 6 points.
Next step after this mating will be the integration of the solar array sun shield, which will happen around May this year. And at that point, the satellite will be in full flight configuration. And at that point, we will go to Cannes to conduct the environmental test campaign for about 6 months. The objective is to have the satellite completely integrated and validated at the beginning of next year.
After the mating, the next step will be the finalization of all the connection, electrical testing. Then in front of the telescope will be installed the sun shield and the solar array, and after that the eye gain antenna. Then the test campaign will start in Cannes. The full spacecraft will be tested in environmental condition, and at the end it will be ready to be shipped to Kourou for the launch campaign.
Launching around the same time as Euclid is NASA's SPHEREx mission. It will survey hundreds of millions of galaxies near and far, some so distant their light has taken 10 billion years to reach Earth. Also, it will search for water and organic molecules within the Milky Way.
SPHEREx is NASA's latest Explorer mission in astrophysics. It's a small telescope, but it has this unique and powerful capability of doing spectroscopy everywhere.
We are going to survey the entire celestial sphere and collect a data set that will help us answer 3 fundamental science questions.
It's going to tell us about the origin of the universe, the birth and formation history of galaxies, and the abundance of essential molecules such as water in the early stages of star and planet formation.
The great thing about SPHEREx is not only will we view the entire sky 4 times, but we will see it in nearly 100 near-infrared colors. And that's really never been done before.
According to our current understanding of the universe, we think that in the very earliest times, and I'm talking here a fraction of a second, much less than a nanosecond, the universe appeared to have gone through an accelerating expansion called inflation. And this is really a profound idea, and we're very interested to test it. And so one way to do this is to look at how matter is distributed over the universe. We want to map hundreds of millions of galaxies in 3 dimensions. What SPHEREx does, in addition to mapping out all these galaxies, is we cover the whole sky. So we can measure these galaxies over the largest part of the range we can see, which is the entire sky. And we want to cover the full range of distances from today to as far back as we can see.
We know there are about 100 billion galaxies in the universe, maybe more, but we still don't have a good understanding how these galaxies came to be. Did they all form at the same time? Did they change in size and luminosity or brightness over time? So the intent with SPHEREx is for us to figure out the formation history of galaxies, where do they exactly form, and how do they grow over cosmic time. And that information is crucial for us because that'll allow us to separate various theories we have right now on the formation and growth of galaxies.
SPHEREx will also identify targets for more detailed study by NASA's James Webb Space Telescope and the future Nancy Gross Roman Space Telescope. The Nancy Grace Roman Space Telescope is set to launch atop a SpaceX Falcon Heavy within the next few years. It will capture images unlike any satellite before it. The Roman Space Telescope will have the same image resolution as Hubble, but with 30 years of technological advancement, will cover an area 100 times larger. Roman will also view the sky in carefully selected wavelengths of infrared light. This will allow scientists to see through the obscuring dust to reveal hidden stars and watch the growth of galaxies over the last 10 billion years. Because Roman will be seeing further back in time, accurate measurement of distant stars is critical. A small galaxy close in looks similar to a large galaxy farther out. One method used by astronomers to gauge distances is something called a standard candle. A standard candle is a type of stellar object or event that emits a specific known amount of light. This works because light sources appeared predictably dimmer the farther away they are. So, for further distances, astronomers have to rely on the brightest of stars or events, in particular exploding stars called supernovae. There are a few different kinds of supernovae, but the best for standard candles are type 1a. These supernovae involve a white dwarf, the leftover core of a dead star, and one other star in a binary system. The white dwarf accumulates mass from its partner and eventually explodes, giving off a set amount of light. These beacons then allow scientists to accurately predict their distances. Roman will also use its broad view to search for planets around other stars in our galaxy. It will be fitted with a coronagraph which reduces the light coming directly from the star to separate it from the light reflected by the planet. The Roman Space Telescope's coronagraph doesn't block the star's light. It uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly disappear, revealing brighter planets. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own. The Nancy Grace Roman Space Telescope will also look for the fingerprint of dark matter and dark energy in the distant reaches of the universe. With an unprecedented combination of breadth and depth, it will open a new era in observing and understanding our universe. Black holes, where time and space converge under gravity's immutable power. These extremes of nature, once considered improbable, are now giving up their secrets. In fact, scientists have been able to imagine the impossible, the black hole at the center of our galaxy. We can now peer into the abyss. The concept of black holes was first proposed by the German astronomer and physicist Karl Schwarzschild, barely a year after Albert Einstein had published his works on the field equations of gravitation in 1915. Schwarzschild wrote to Einstein from the German trenches of the First World War, detailing his mathematical results of his gravitational equations. Sadly, the brilliant scientist later succumbed to a skin disease he contracted in the trenches at the age of 42. The existence of these so-called frozen stars was written about and debated for 50 years. In 1967, physicist John Wheeler coined the term black hole to describe these impossible objects and the conditions that would create them. New Zealander Roy Kerr advanced the concept by publishing a solution to the equations, which would require that black holes spin like all other astronomical bodies. Then Stephen Hawking and Roger Penrose theorized that black holes could emit radiation, now called Hawking radiation. The theory: if a black hole had no material to absorb and grow, then a black hole could evaporate, effectively shrink, and die. All scientists had to do was find one to study. Quasars, the tremendously bright, distant objects, were factored in as a strong case for black hole accretion, the only imaginable energy source capable of such incredible luminosity. In 1964, astronomers discovered one of the brightest X-ray sources in the sky in the constellation Cygnus, and labeled Cygnus X1. The powerful source didn't coincide with any bright optical or radio source, leaving it in the mystery basket of observations. Before long, with advancements in computers and space-based telescopes like Hubble, black holes were eventually detected, or their effect on their surrounds were detected, as black holes by their nature can't be seen.
Black holes are these incredibly fascinating but mysterious objects. We know they sit at the hearts of galaxies, and they drive how those galaxies grow and how those galaxies die. They swallow gas and stars up. They're also these incredibly enigmatic and mysterious objects that live at the boundary between our two great theories of physics: general relativity, which describes gravity, and quantum mechanics, which describes the smallest things in the world.
Black holes are literally gravity run amok. They are purely gravitational objects predicted by Einstein's theory of general relativity, and their most notable and terrifying feature is that things go in and they never come back out.
Wonder comes to my mind first. Such objects were never expected to exist in nature until very recently. As a matter of fact, I was a complete skeptic about black holes as recently as 20 years ago.
Black holes are places where Einstein's theory of general relativity is the whole story, not merely a perturbation on top of Newton's theory, which explains the dynamics of planets in our solar system. As a result, black holes provide a unique environment in which to probe general relativity specifically and strong gravity generally, and its implications across the cosmos.
If you want to make a test of the fundamental theories of the universe, you want to go to the most extreme laboratories in the universe. And a black hole is that.
Seeing a black hole actually allows us to not only know they exist, and not only know an event horizon exists, it also allows us to test some of the very basic predictions of the theory of general relativity of Albert Einstein, which really describes space and time in its completeness. And that has never been tested before.
If you like Einstein's theory of gravity, then black holes are, one of the most interesting examples of this theory. And this is my role within this project. I am a theorist. I work with equations and simulations, and my role is that to try and understand whether the image that we produce corresponds to the predictions of Einstein's theory or maybe to something else.
From the physics side, I find that more an interesting question, that this is basically some kind of rent or tear maybe in space-time, and a place where we don't understand the physics and have a lot of serious questions about information theory.
I was very excited the first time I saw the first image. For a long time, this was purely theoretical. We were predicting that we would see certain features in the image, but we didn't really know, was it really there? And now we know, and it was exciting that all of that uncertainty collapsed in that moment.
So as the magnetized gas is falling onto the black hole, it heats up and therefore generates the light that we then see. Now, from our daily experience, we expect that light travels on straight paths and straight trajectories. We call them rays. Here, the situation is very different. We have a black hole sitting right there. So what the black hole is doing, it is deflecting and bending the light rays away from the straight paths that we understand in our daily life. And in fact, it can be so strong that we can see things that are behind the black hole that we thought are obstructed by it, just because the black hole is bending the light rays into our line of sight.
Scientists began running simulations on supercomputers. Multiple computational models were visualized to better understand what they might find in the data collected from their observations.
After we computed the radiative signature of our simulations, we have to compare them to the observations. And this can be imagined as you're in a stadium during a football match, and you have an image. And you want to figure out if this person or whatever is on this image is among the spectators in the stadium. So what you do is you take this image and try to match it with all the 60,000 spectators in the stadium. And you do this while you rotate it, you scale it, you increase the contrast, and you try to figure out first what is on your image. Is it a person, is it a cat or whatever? And try to match this to the spectators. And this seems trivial, but it's not. It's a highly computational, demanding process. So we need a supercomputer, which we have in Frankfurt. And we developed a so-called genetic algorithm, which is a very smart way running through these images and try to adjust them. And this takes roughly a month. And after this calculation time, we have maybe 10 of those spectators which match your image. And this is very similar to what we do in the EHT. So we try to compare and match our observations with the theoretical predictions.
So what is most surprising of this experience is that we managed to get a very good image the first time we tried to synchronize all of these telescopes at the same time. It is not so surprising that we obtained the image that we had predicted through simulations, because, well, we believe our simulations are correct, and because we believe that the theory of Einstein's general relativity is the correct one.
In 2019, they achieved their result, an image of the shadow of a massive black hole in the distant M87 galaxy. It was a world-first achievement celebrated around the globe.
I think we've been extremely lucky. I'd expected that we have to work for years and years, do many observations until we get a final image. And then we look at our first source and we see that ring. We see the event horizon and we see that shadow, that dark region, and you know immediately we are looking at an event horizon and a black hole from all sides at once in this thing. We see at a region where time stops. This is a very different part of the universe that we're seeing for the very first time.
We wanted to take an image of a black hole, and the problem with black holes is that they are very small. So you want to take a very big black hole, which unfortunately is very far away from us. And so you need a big telescope. This telescope is 100 meters in diameter, but it's not enough. You want a bigger telescope, and of course it's impossible to build, but you can create a virtual telescope by joining different telescopes in different locations, and so you can build a telescope which is as big as the Earth. And in fact, that's exactly what we've done. We joined telescope like this with telescope on the United States, and one even in the South Pole, to get a very sharp image, an image that is comparable to seeing an orange on the moon. Black holes tell you that there are regions inside them that cannot be explored. And for a physicist, this is very disturbing and attractive at the same time, because we don't like to have doors which we cannot cross. And in particular, inside black holes, physics is even expected to fail completely. And so this even adds fascination to these objects.
The future of the project will hopefully going towards a new understanding of more fundamental questions in physics. If this is true that black holes are the extreme objects where we can study gravity, and we know that general relativity, which describes black holes in the outer part up to the event horizon, breaks down at the event horizon. So the big hope is that with more data we might be able to study the physics beyond general relativity. So maybe there might be quantum physics ruling beyond the event horizon, or the combination of quantum physics and general relativity, which would be the theory of quantum gravity, which is non-existent at the moment, but we might learn more about this with the help of studying black holes.
Our experiments are like an Arctic expedition. We have to plan for months and months and months in advance, gather our equipment, and then we have this great migration of people to observatories all around the world. We stay up all night, we run our telescopes, and then we have this terrible period of waiting where we don't know if it's all worked. We send all of our data together, and only when it's truly combined do we know if it's worked. And then the even harder part begins of analyzing that data and being very, very careful, doing all the checks and balances to know that we got it right.
Data analysis, imaging black holes, and doing simulations is very exciting. It's also very difficult and requires a lot of patience. It's a very long process, but seeing the final product is very satisfying.
The Event Horizon Telescope collaboration is this amazing group of fantastic people from all around the world. Americans, Europeans, people from Asia, who've come together with all their technical expertise and scientific expertise to make this image of a ring around the black hole. The future of this project is amazing, because now that we've seen what we're after, we have so many more questions to ask about it, to push into the regime of, can we decide, is Einstein right? Can we study how gas really gets swallowed by the black hole? Can we see a giant eruption of radiation, of particles coming out of the system? So many things to do. We've really only just begun.
Now we want to make the first movie. Now we want to understand how space-time rotates around the black hole. We'll do that by putting more telescopes around the world to make our virtual lens even better.
It was a fantastic way of combining talents from different people in a way that otherwise would have not been possible. In order to take this picture, you need the cooperation, the simultaneous observations of many radio telescopes across the planet. You need to have the largest possible network of telescopes taking the same image at the same time.
New goals for the Event Horizon Telescope were quickly set. The M87 massive black hole is far away from Earth. Scientists wanted to get a closer look and decided to image another black hole at the center of a galaxy, one much closer, but also much smaller and shrouded in gas and dust.
So if you try to look into the center of galaxies, it's usually blocked from view by dust and other stuff. In the radio, you can look through, like here today, we can look through rain, you can look through clouds, and then we can look through dust. And with combining radio telescope like this together with other telescopes in the world, you can peer right into the center of the galaxy and see this black hole.
The science result is it's just one point in time in the project, and we are always learning more about how the instrument works, how people work, how new theories come about, and so this is an evolution in my perspective. It's not just one point in time where you say, this is it, that's done. It always continues.
So we still have a lot of mysteries to be solved, problems to be tackled. There are still many questions about black holes, so I would like to study further the black holes.
The Event Horizon Telescope targeted the black hole in Sagittarius A, which is the location of the center of our very own Milky Way galaxy.
The long-term future of experiments like the Event Horizon Telescope is moving this kind of instrument into space and starting imaging black holes from space, which improves a lot this kind of observation because it allows us to have even higher angular resolution than what we have now. So we will be able, maybe in 20 years, 30 years, make a very accurate images of the event horizon of a black hole.
Not only did scientists image the black hole, they sampled the radio emissions from the surrounding hot gases, giving us an audio impression, the sounds of a black hole.
So far, we've been looking at the closest massive black hole, but quasars, very distant from us, with gravity, we can see the motion of gas and resolve the sizes of these regions and thereby measure then the mass precisely. So if you can do this for many quasars, many distant objects, then you can solve perhaps the riddle how massive black holes played a role in the evolution of galaxies. We now know that basically every galaxy has at its center a massive black hole of different masses. We'd like to understand that in detail. There is, if you like, a symbiosis between these black holes and galaxies, and we need to understand that in order to understand the evolution of the universe.
Studying the data from the Event Horizon Telescope continues to reveal more detail. In this case, X-ray emissions reveal magnetic lines of force through the orbiting gas clouds. Further study of the X-ray emissions is currently underway with a new space-based X-ray observatory, the Imaging X-ray Polarimetry Explorer, or XP. Launched in 2021, XP is designed to observe extreme cosmic objects like pulsars, neutron stars, and black holes. This satellite is able to study X-ray radiation, which is polarized or oscillating in a particular direction. This reveals more detail of the physics of these high-temperature environments particularly around black holes.
But there are two other parameters that we could look at if we only had the tools to do that, and those have to do with the polarization, the degree of polarization, and the position angle, the angle associated with the polarization. So by doing this mission, we're opening up 2 more degrees of freedom to be able to try to understand how are the X-rays produced, what are the models. We have to be able to predict the polarization that we will turn out to measure. So it's really exciting. Our science working group has studied we have 7 different teams of studying different classes. So for example, the radio pulsars, supernova remnants, etc. And so we're going to be looking at 7 different classes and several examples of those classes, so that we get a good preliminary survey of what polarization is out there.
The extreme environments created by black holes are an opportunity to study many other phenomena. Neutrinos, the most abundant particles in the universe, have almost no mass and very rarely interact with matter. They seem to be generated in extreme objects like exploding stars and the fast particle jets ejected by supermassive black holes. Colliding black holes are another event closely watched, as they generate gravity waves that ripple through space-time and can be detected here on Earth. Another recent event detected was the flipping of the magnetic field surrounding a massive black hole. The reversing polarity caused the visual brightening of the material surrounding the black hole and the reduction of its X-ray emissions. During this time, the X-ray corona disappeared, and only when the flipped magnetic field gained strength did the X-rays emissions recover. Another black hole has been observed devouring a star that wandered too close. The ejected superfast jets of material interacting with nearby dust clouds and aiding to form planets within the material. These singularities appear to be an intrinsic part of both the destruction and creation of stars and planets. While we don't have all the answers, discoveries like this one set us on a path to understanding more about the universe. It is one of the most complex and sophisticated scientific instruments ever built. It is orbiting our Sun 1 million kilometers out in space in temperatures of -266 degrees Celsius. It is a time machine that will peer deep into the past and reveal unexplored reaches. And it will be our key to understanding where we fit in this enormous universe. Launched aboard an Ariane 5 rocket, the James Webb Telescope has successfully reached its destination, unfurled, and begun its great adventure.
Hubble revolutionized astronomy. Hubble showed us the early universe. Hubble showed us what the universe works like. And as these revolutionary findings came along, people realized we need a next generation space telescope. This was 25 years ago, and this is how Webb came into being. Now, you can see 25 years of development time. This is not unusual for a large space mission, from the first idea to fruition, to the launch. And this is why these missions are really once-in-a-generation launches. We are witnessing something particularly special that an astronomer typically gets to witness once, if they are lucky, twice in their entire career.
James Webb Space Telescope is a collaboration between NASA, ESA and the Canadian Space Agency. So altogether that's 24 countries, lots of industrial companies, academic institutions, universities, and thousands of scientists across the whole world are now waiting to use the telescope. So by combining the power of the best in engineering and science from all of those countries in this international collaboration, we can do much more together than we could do on our own.
The origin of Webb is the search for our origins. We want to find out where the first galaxies formed, how they formed when they started making their stars in the very early universe not long after the Big Bang. And to do this, Webb uses its big mirror and its infrared vision to look into these really early days, observe the light from these galaxies that's been traveling to us for billions of years, and it shows us these galaxies how they were billions of years ago.
Sure, so infrared is a longer wavelength than visible light. So we can't see infrared, but James Webb can. And what's important about an infrared telescope is it allows us to see through clouds of gas and dust and see the planets and stars and galaxies that are beyond. In addition, James Webb has a larger mirror than Hubble, so it can see back further in time, and it's orbiting at a different point.
James Webb is very complementary to everything that has been done before, to Hubble, to Herschel, but will be a huge step forward just because the collective area is huge. 6.5 meter is pretty impressive. Hubble, as a comparison, was 2.4. So we're talking of a collective area which is much bigger, much more sensitivity. We say 100 times more sensitive. With a complement of state-of-the-art instruments which will take images and spectra in wavelength regimes that we haven't explored as much from space up to now.
The telescope houses 4 scientific packages: MIRI, a mid-infrared instrument, the near-infrared NIRCam, NIRSPEC, a spectrographic analyzer, and the NIRIS imager and guidance sensor.
The near-infrared spectrograph, or NIRSPEC, it's one of the 4 scientific instruments that we fly on James Webb Space Telescope, or Webb Telescope. It's very important because it will allow us to analyze the light of the astronomical objects we will observe. A spectrograph works very much like a prism. In fact, there's a prism inside our instrument and gratings, and they, like the prism, splits the white light into its rainbow colors. These instruments will split the near-infrared lights from the astronomical object into its components. And this is very useful to scientists because from that they can understand the physics of the objects they are observing, what are the temperature, the elements, the physical condition, and therefore we can understand what's going on the objects we observe. So we will observe all sorts of astronomical objects, from galaxies, and the focus is very much on very far away galaxies that are 13 billion light years away from us, so back in the far past, that they were forming soon after the Big Bang, from very what we call nearby objects, which are not really nearby, but they are exoplanets in stars around our neighborhood, the neighborhood of the solar systems in our galaxy. So this is the type of objects we will observe, and investigations. It's about understanding what are the atmospheric condition on the exoplanets, or what are the physical condition of the galaxies we observe far away. So, going back to the very far away galaxies, this instrument NIRSPEC will play a crucial role in the, observing this far away galaxy and telling us what is the physics. So again, what are elements are present, in which proportion, what are the temperature, and that is fundamental if you want to understand how galaxies form, which is one of the big questions we have in astronomy. We see trillions of galaxies around us, how all these galaxies formed. And with this instrument, we can piece together more of the puzzle. It complements the other instrument because of its function of a spectrograph. So on the Webb telescope, we have cameras, other type of spectrograph, one particular MIRI, which is also a partially European instrument, which will focus on the mid-infrared light. Near-infrared is the focus of NIRSPEC. Analyzing the light that comes from astronomical objects in the near-infrared wavelength range. While with the camera we see images, so we detect the objects and we know where they are and what are the main characteristics. With NIRSPEC we focus really on certain objects and analyze the lights and split the lights into its components, and with that understand the physics of the objects we are observing.
The telescope is in a halo orbit at the L2 or second Lagrange point and is orientated away from our Sun, with the sun shield keeping the instruments at their very low operating temperatures.
Where is the telescope pointing relative to the spacecraft? So we waited for the near-infrared camera to get the detectors cold enough so that we could take images, and we did some evaluation of that. And once we were convinced that it could take images, we were really trying to determine if we pointed at a bright isolated star, where's the telescope pointing? So we picked a star that was very bright and didn't have any stars near it that would contaminate the image. We know that the primary mirror segments aren't aligned yet, so they actually act like 18 separate telescopes, and we expect to see 18 separate images, one for each mirror, that are a little bit blurry at this point because we haven't aligned or focused anything. And so we pointed at a bright star and we made a mosaic. We actually took the near-infrared camera and we took images in different parts of the sky, and then we looked for the 18 spots from the 18 different telescopes, if you will, and we were very excited to find them. They were actually very close to where we were pointing, well within our expected size of where they might land. And the 18 spots were actually fairly close to each other as well. So really everything was very close to what was predicted and much better than what we considered to be the worst case pointing. So we were really excited about that.
Over the following months, each individual mirror was adjusted and focused, then aligned together to create one single image. The alignment image of the single bright star gave an indication of the power of the Webb telescope. As seen here, behind the bright star, the image captured numerous distant galaxies. The science team then captured several sample images of different objects.
The first images from the James Webb Space Telescope are designed to demonstrate the full range of the capabilities of the telescope.
Scientists then sat down and studied these many test images, which amazed the team.
The cluster is, it's probably bigger than that. There's lots of light. Yeah. But I think when you stretch the background, we didn't dare to say. You should have said it. This is all Iraq. It's going from the 70s into the 80s and 90s. Even in your camera, it really stays the same in all wavelengths.
We're seeing a sample of the amazing science that Webb will be able to do over the coming years. Remember, it's just a sample. So we are seeing scenes and vistas from across the universe, toward the first galaxies, to stellar birth and stellar death. And we're seeing an exoplanet spectrum for the first time with Webb, showing water or steam in its atmosphere. So here, what we're seeing in this deep field image, Webb's first deep field, is massive
cluster of galaxies, and what this cluster does is it bends the light from even more distant galaxies coming behind it, and you can see that as sort of bananas or streaks in the field. And this field allows us to look for some of the very first luminous structures in the universe, the first stars and galaxies, and this was one of the reasons that Webb was originally built. So with the Southern Ring Nebula, the image here, what you see is a star that is similar to our own sun, but 5 billion years in the future when it dies. And so when stars like that die, they push off the outer atmospheres, and this gas cloud you see is filled with elements like carbon and oxygen, kind of elements that we are made of. And this is how dying stars seed the galaxy with these elements that ultimately are important for the formation of life. So here we are seeing a small group of galaxies that what we call interact, they're actually colliding with each other. And this is a very fundamental part in the evolution of galaxies. They bump into each other all the time. And when they bump into each other, they create shock waves. And in these shock waves, you have this tremendous formation of new stars. And you see these shock waves in this image here, and you see the formation of stars there.
Yes, this is a set of galaxies that are sort of locked in a cosmic dance. And so they're moving, and two of them are merging, and we can see all of them moving around in that and their interactions.
You also see the galaxies superimposed on this field of distant galaxies in the background, whose light has probably traveled through the universe for billions of years. And so this is very typical for Webb images, that everywhere we look, we're going to have these distant galaxies in the background.
And one of the main things that we want to look at with the James Webb Space Telescope is the most distant galaxies in our universe, the furthest objects away. And that also means that they were the first objects to form after the Big Bang, the first stars and galaxies about 13.5 billion years ago. The reason that all of their light is now in the infrared is because the universe is expanding. And as it expands, the light from those most distant objects gets redshifted to infrared wavelengths. So again, Hubble can't see them, but the James Webb Space Telescope is designed exactly to see these very distant, very faint objects.
Those emission lines, yeah.
Oh yeah, this is such a beautiful image, and maybe my favorite. What we see here is a stellar nursery, a cloud of gas and dust that is actively forming new stars. And you see this as sort of a landscape that looks like mountains because the cloud is being eroded away by hot stars that's off the field to the top. And they're cooking off the cloud. And as they do that, they push on it. And so what that means is that you can form new stars sort of close to the surface of the cloud there. And you can see those stars popping out. And you can see them also create jets and outflows as part of this process that move through the cloud and create these streaky structures in it.
In comparison, the Hubble imagery here captures the visible light. Now, compared to the Webb images, you can see the dark dust turn transparent, revealing what is within and behind the veil.
I'm really excited about James Webb and the spectroscopic capabilities. It's absolutely revolutionary, the sensitivity and the resolution we can get to look at the dust and the forming stars in some of the very most distant galaxies to us, where we can actually see individual stars and work out what the chemical compositions they're producing in terms of dust and the minerals they're producing and the life cycle of matter in the universe, that chemical evolution of galaxies. And no other instrument, no ground-based instrument can do this because of the atmosphere. Only space-based instruments can do this. And previously, the previous generations have been so small they've been able to only look at galaxies in the Milky Way or in the Magellanic Clouds. But James Webb will be able to push that envelope out to lots of galaxies in the local group, and so we can look at very different formation scenarios towards the early universe. So that's what I'm most excited about, is these dying stars and forming stars.
The hope is Webb will be able to see so far back in time, it will reveal the very first galaxies and stars created after the Big Bang.
Lots of big questions. How do galaxies evolve? So the Hubble Deep Field has given us some hints of what we think is happening, but we haven't been able to see it in enough detail or with enough galaxies to really know. So it's going to fill in, almost you could think of it as a gap in time between the Big Bang and the galaxies we can study with Hubble, and we'll find galaxies that are in that gap.
This image is of the spiral galaxy IC 5332, which is over 29 million light-years away. The infrared web sees through like an X-ray into the interior structure of the galaxy.
Well, it's going to allow us to understand every phase of cosmic history for the last 13.5 billion years. So we'll be able to answer questions like, how are galaxies formed and where do we fit into the cosmos? We'll be able to see the formation of stars and planets. We'll also be able to understand atmospheres of exoplanets.
The James Webb also captured images of local residents in our own solar system. Here is Jupiter seen in the near-infrared. It reveals the polar auroras and the heat signatures deep within the clouds of our largest neighbour. Here is Neptune as never seen before, its rings clearly visible along with several of its moons. The most prominent features of Neptune's atmosphere in this image are a series of bright patches in the planet's southern hemisphere that represent high-altitude methane ice clouds. More subtly, a thin line of brightness circling the planet's equator could be a visual signature of global atmospheric circulation that powers Neptune's winds and storms.
I think the great thing about Webb is that it actually touches all of astronomy. So because it's so flexible, you can use it to study things inside our own solar system, but you can also use it to find examples of the very first galaxies. So it really is spanning almost the entire history of the universe. So it's really going to be transformative to lots of different areas. I think the two areas that are going to be transformed the most are my own field, which is finding and understanding these very early galaxies, and then on the other end of the scale, actually looking at planets around other stars that are relatively nearby to us. But I think every single astronomer in the world will ultimately be taking some of the results from Webb and incorporating it into their own research.
Astronomers have made giant steps in our understanding of the universe over the past decades, but there remains much to learn about our cosmic origins, and the range of questions waiting to be answered is causing high expectations.
Webb is more than tens of thousands of scientists. Webb is 8 billion people looking for the origins.
The search for life within our solar system continues unabated. Scientists are following the signs for water, either deep oceans or hot springs where life can evolve. There are exciting candidates to explore: the icy moons of Jupiter, oceans in the sky. Orbiting the giant Jupiter are 3 prime candidates. Ganymede, the largest moon in the solar system. Callisto, once thought to be dead, may harbor a salty ocean. And the active Europa, with its plumes of water erupting into space. The European Space Agency is about to launch a probe to investigate these 3 potential sites. A daring mission called JUICE.
JUICE is the Jupiter Icy Moon Explorer. So it's the first large mission of the Cosmic Vision program of the European Space Agency, and has the objective to study the Jupiter system and 3 of the Galilean moons, 3 icy moons, which are Europa, Galileo, Ganymede, and Callisto.
This mission is of particular importance for the European industry because this is the first time that Europe is going to Jupiter. So we are supporting the European Space Agency and beyond the European scientific community in their endeavor to go to Jupiter and explore Jupiter and their moons.
The scientific objectives of JUICE are multiple. So first of all, humanity always poses itself a question: are we alone in the universe? Is there life outside Earth? To respond to this question, first we need to answer to another question: are environments where life can be sustained before going and search for life? And this is one of the main objectives for JUICE, to search if on the environment, on the ocean world of Europa and Ganymede, there are the conditions to sustain life. Now, from the past missions, we know that some of these conditions are fulfilled, and we want to go with JUICE to investigate even deeper and to make sure that these conditions are there. And these conditions are, for example, there is water, there is liquid water, there is a source of energy inside the planets, so there is energy. There are the chemical compounds which are needed to sustain life, the life as we know, so based on carbon. And is a protected, is a stable environment because it's under the crust of the moons. So once these 4 elements are fulfilled, there is the probability that life will be sustained outside Earth is very high. The other objective of JUICE is to study the Jupiter system in its integrality, as seen as a miniaturized solar system, if you want. We have a gas giant with bodies that go around this body, and studying the interaction of the gas giant with these bodies, we can understand better, for example, the development of our solar system, how it was born, how it works, and etc.
So JUICE is a very exciting mission. So we are going to explore Jupiter in details. And in particular, I would like to know whether there are conditions hospitable for life around a gas giant like Jupiter. And we are going to focus that on the 3 icy moons, which are Europa, Ganymede, and Callisto. And we would like to know whether inside those moons there are conditions which are interesting for life. And we are going in particular to explore the liquid water which are underneath the crust of those moons.
In the past, there were other missions that they analyzed the Jupiter system, like Galileo, for example, has given us important information to build the JUICE mission. There is also Cassini that passed by, that we gather a lot of data also from it. And also from observation from Earth, also observation from Hubble, for example, has provided us a lot of data which are precious to build JUICE and to build also the profile of the mission, to know what we are going to study.
We have in total 10 scientific instruments on JUICE, and basically we will observe Jupiter and its moons in all possible wavelengths and type of observations that we can do. So we have a number of telescopes in all wavelengths, visible, infrared, ultraviolet. We have a radiometer to sense the atmosphere, the structure of winds of Jupiter and their moons. And we have electric and magnetic sensors. Some of them will be deployed at the tip of a magnetometer boom. So RIME is this big antenna that you see there, deployed just behind us. It is a radar antenna that is working at a very low wavelength, 9 megahertz. So for that to happen, you need a very long piece of antenna that will be able to sound very deep below the surface, the internal structure of the moons, in particular Europa, Callisto, and Ganymede. The objective is to try and locate the liquid water ocean that is underneath the icy crust of these moons. As of today, we are still not sure how deep we have to dig, let's say, to find this ocean, and this antenna will help us figure out at which depth we can find this ocean.
At the moment, the nominal science is foreseen to last 4 years. In these 4 years, Jupiter will make all the investigation. It will make some flybys of Europa, flybys of Callisto, and then we'll go into the details of the analysis of Ganymede. We stay in orbit around Ganymede for a good part of the Jupiter tour.
JUICE will start its science mission about 6 months prior to entering orbit around Jupiter, making observations as it approaches its destination. Once in the Jovian system, a gravity-assist flyby of Jupiter's largest moon, Ganymede, also the largest moon in the solar system, will help JUICE enter orbit around the gas giant. During its operations, the probe will make 2 flybys of Europa in July 2032. Europa has the strongest evidence of an ocean of liquid water under its icy shell. JUICE will study the moon's active zones, surface composition, geology, and the plasma environment around the moon. A sequence of Callisto flybys will then be used to study this ancient, cratered world that may also harbour a subsurface ocean, but will also change the angle of JUICE's orbit, making it possible to investigate the polar regions of Jupiter. Now that the probe is fully assembled, it has to be thoroughly flight tested to ensure its survivability, because the giant's magnetosphere traps an intense and dangerous radiation environment.
This milestone is very important because here we have the spacecraft. It's integrated, it's ready. We have all the 10 instruments are delivered, are there. All the platform units are there, the antennas is all in place. So the spacecraft is ready for the test campaign to verify finally that everything's work as expected within the performances they are expecting. and this is 1 year from launch. So this is a very important milestone. The spacecraft integrated is there, and we can carry on with the test phase.
So we start first with electromagnetic compatibility test. The goal is to verify that the spacecraft has a sufficiently low level of electromagnetic perturbations, because a number of instruments of JUICE will sense electric and magnetic fields at Jupiter, and we do not want the spacecraft to be a source of perturbation for that. After that, we will do a number of mechanical tests. It will be done over summer. Here the goal is to verify that the spacecraft can survive the launch environment that will be imposed by Ariane 5 when we will launch to Jupiter.
It is true that the JUICE spacecraft that we can see on the background is going to be launched in space, meaning that it's not like for aircraft. We can repair something after a couple of hours of working. We need to make sure that before we launch, everything will work properly as expected.
And then there will be additional tests, like a vibration test, including with the solar array, so that will be quite exciting. We have also what we call EMC test, so to make sure that the spacecraft is quiet from the electromagnetic point of view. It's very important for the science of the mission. And additional tests like communication between the spacecraft and the ESOC flight control team that will need to control the spacecraft once it flies. So all these tests will take place in the coming 10 months. And after that, hopefully the spacecraft will be declared ready for launch, and we will ship the spacecraft to its final destination on Earth, which is the French Guiana spaceport.
Replicating the environs of space is no easy task here on Earth. At ESA's test center, ESTEC, in the Netherlands, is the Large Space Simulator, which can model the vacuum of space and simulate both the extreme heat and cold of deep space. It is Europe's largest vacuum chamber, and its internal black panels, which are filled with liquid nitrogen, were used to cool the environment down to around -180 degrees Celsius. To test against extreme heat, lamps are used to raise the temperature up to 250 degrees Celsius.
JUICE, in order to fly to Jupiter, will do some gravity assist around several planets, among them the Earth and Venus, which is very close to the Sun. And in fact, all the electronics inside the spacecraft are supposed to work properly in a certain range of temperature, and the thermal design of the JUICE spacecraft aims at protecting this unit from the very harsh environment, cold or hot, for this unit, in order for them to work properly when we will start to do science at the Jupiter icy moons.
To reproduce the heat side of space, so when we go close to the Sun, we simulate the Sun. And in order to do so, we have a set of lamps, very powerful lamps, that are reflected in 121 mirrors that can be reconfigured depending on the mission characteristics. And in this case, we simulate the heat of the Sun while the spacecraft goes through Venus. Why Venus? Because the JUICE mission is doing a flyby in Venus before going finally to Jupiter.
Yeah, so when I saw JUICE going to the space simulator, I had a mixed feeling, of course, because it was a very scary moment. It's a little bit like your baby spacecraft, so you're a bit scared that something will go wrong. But at the same time, you know that the team, in particular, the test center people, they know what they are doing, so it's quite a secure activity. So it was a mixed feeling, but you always feel nervous when you see the spacecraft going into the Large Space Simulator.
And in addition to that, we have also some requirements coming from the environment itself of Jupiter, like temperature and radiation. Jupiter is a very aggressive radiation environment that is making the whole design of a spacecraft even more complex.
Jupiter has the largest magnetosphere in the solar system, 18,000 times more powerful than Earth's. In combination with the sulfur dioxide ejected by the Moon, the space around Jupiter is loaded with plasma. The magnetosphere also traps and accelerates particles, forming an intense radiation field that is thousands of times more powerful than Earth's Van Allen belt. The result is a very hazardous environment for spacecraft and potentially humans.
After that, we will also test the propulsion system in order to be sure that it is leak-tight and fully operational when placed into a flight configuration. We will do a second thermal vacuum test in a chamber very close to this facility in October in order to verify in pressure and temperature conditions and full flight configuration that the spacecraft is behaving nominally in all functions. And finally, after having tested the spacecraft in all these various environments, we will verify a last time that from a functional perspective, the spacecraft behaves nominally and is ready for shipment to the launch site.
That launch site is Europe's spaceport in Kourou in French Guiana, where the venerable Ariane 5 will lift JUICE into space. It will also be the final launch of the Ariane 5 rocket series, one of the most reliable launch systems, with 112 launches and just 5 partial or complete failures. The Ariane 5 heavy lift vehicle has launched many of the most important space probes, including the Rosetta mission and most recently the Webb Space Telescope. It will be replaced by the Ariane 6 heavy lift booster.
JUICE will be launched next year in 2023 in April, the beginning of April. The launch window will open on the 5th of April and will stay open for about 3 weeks because of celestial mechanics. And then the spacecraft will, before being injected into the transfer orbit to Jupiter, will have to acquire more speed, and we will need to do a certain amount of gravity assist to the inner planets of the solar system. We will do a gravity assist, which will be a first, which will be a Moon, Earth gravity assist, then there will be a Venus gravity assist, other 2 flybys of Earth, and then we'll be projected to the insertion orbit to Jupiter for other 2 years. So overall, it will take about 8 years to get to Jupiter.
The gravity assists, 25 in total, will allow the probe to gain the necessary speed to reach its final destinations without consuming the 3,000 kilograms of precious fuel reserved for course corrections and orbital insertions. JUICE will arrive at Jupiter in 2031, followed by a proposed orbital insertion around Ganymede in 2034, all part of the European Cosmic Vision Programme.
The Cosmic Vision Programme has an objective of studying also outer worlds, so it will be complementary to future missions, to mission currently in development, like Plato, like Ariel, like SMILE, and be complementary with the future missions. There will be an Envision for the study of Venus, with Athena, for example, for the study of the universe, with LISA for the study of the gravitational waves. So it will be complementary to have a full and round information on astronomy and planetary science. And it will be also part of the inspiration that the Cosmic Vision Programme wants to transmit to the scientific community and to the public. So JUICE has been developed by a huge industrial consortium to build the spacecraft itself. So in particular, we have Airbus France, which is the main contractor to build the spacecraft, and which is made 95% by European companies. It's about over 100 companies from Europe, and about the 5% of contribution from United States. The JUICE embarks 10 scientific payloads, and the payloads are the contribution from leading funding agency, which are the space agencies. So in particular, we have CNES, There is the Italian Space Agency, DLR, German Space Agency, there is the UK Space Agency, Swedish Space Agency, and we have also contribution, an instrument, another contribution from NASA, as well as from JAXA, and also from the Israeli Space Agency. And each of these scientific consortium is built by other institutions from as well over Europe. So we have also contribution from Austria, from Belgium, from is a European-wide consortium.
Over time, JUICE's orbit around Ganymede will naturally decay. Eventually, there will not be enough propellant to maintain it, and it will make a grazing impact onto the surface in late 2035. JUICE will not be alone in its mission. NASA is also launching a probe to the same local. However, its primary goal will be to study Europa exclusively. The mission is the Europa Clipper. Due for launch 2 years after JUICE, the Europa Clipper will ride a SpaceX Falcon Heavy. This time, the probe will utilize Mars for a gravity assist in 2025, then Earth a year later, arriving in the Jovian system in 2030, a year ahead of JUICE. Due to the harsh radiation environment, the Clipper will not orbit Europa, but instead orbit Jupiter and make multiple passes of Europa, 44 encounters over 3.5 years. Utilizing the other Jovian moons for gravity assists the Clipper, which will adjust its orbit to pass by Europa and various altitudes from 2,700 kilometers to a mere 25 kilometers, where it will be able to pass through the water plumes erupting from the surface. It will carry 9 instruments, including thermal and radar imaging, ultraviolet spectroscopy, and surface dust analyzer.
This allows us to have a mission that's many years long and to collect and transmit lots and lots of data. As Europa orbits Jupiter, it flexes, and we could measure the gravitational change of Europa by encountering Europa at different points in its orbit. On a typical flyby, we would turn on our remote sensing instruments, we would image the surface, we would interrogate the surface with spectroscopy, and we would do the same thing on the way out. And we would essentially rinse and repeat, and do this many, many times until we understand Europa globally.
Because once we will have investigated whether life can be sustained in the icy moons in Europa or Ganymede, then there could be other missions that will go to analyze more in depth if life is really there, maybe with penetrators, with rovers, with sample return missions. And one of the objective also of cosmic vision is to be an inspirator for future missions. Also for a sample return, for example, why not on the icy moons of Jupiter?
Asteroids, remnants from the birth of our solar system. From planetoid-sized monsters down to tiny pebbles, they have orbited our sun for billions of years. We have seen some up close, even touched their surface. We count their numbers, chart their courses, and keep a wary eye on these mountains in the dark. several spacecraft have ventured out towards these rocky worlds. Some have touched down and taken samples with surprising results, then returned them to Earth. Scientists have found these remnants to be complex and full of secrets. There are different types of asteroids, and 2 new robotic probes are ready to study some of these unique targets. One is called Psyche, and it is perhaps one of the most interesting.
Psyche is an asteroid that orbits the sun out between Mars and Jupiter. It's called Psyche because it was the 16th asteroid discovered, and they were all being named after gods and goddesses at that time.
So the Psyche mission is going to visit an asteroid which is called Psyche. And it is a large metal asteroid, a unique body in the solar system, 150 miles in diameter approximately, and made of 40 to 60% iron nickel metal. That makes it a unique body in the solar system. We visited worlds made of ice and worlds made of rock and worlds made of gas before, but we've never visited a metal world. So we'll get to see something unique and different for the first time.
All the rocky planets that we know of, the Earth, Mercury, Venus, Mars, and the Moon, all have got a metal core in their center. And especially for the Earth, it's the source of our magnetic field, which may be tied to holding onto our atmosphere and making our planet habitable. There's a lot of study that's going on to understand that. But we don't know a lot about our core. What we've learned about it, we learn indirectly because we can't go there. And so Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And so we hope to learn something about what's inside the Earth and other rocky planets by visiting Psyche. But it also tells us about the processes in the very beginning of the solar system. It helps us understand how planets form in the first place.
So the Psyche payload consists of 3 science instruments. One of them is what's called a gamma-ray neutron spectrometer. It's actually 2 separate pieces of hardware. One is the gamma-ray spectrometer and the other one is the neutron spectrometer. Both combined study the elemental composition of Psyche.
If you know the surface composition, what it's made of in terms of iron and nickel and silicon and oxygen, you can then start to say something about its history and how it formed and how it evolved.
By using gamma-ray spectroscopy, we can measure those elements remotely. We don't have to touch the surface. We don't have to dig into the surface.
For Psyche, we're building kind of what we call the Cadillac. It's a very high precision, high sensitivity instrument. It's very similar to the MESSENGER instrument.
That technology that we developed for the MESSENGER spacecraft gave us a huge head start going to Psyche.
For our types of instruments, we don't get to fly them very often. So when we actually get selected for something, that's a big deal for us, where we can, take what we learned from the prior missions and implement it now and make an even better instrument.
Only one body like this that's this big and made of metal in the solar system. So the big mystery is, where did it come from? How was it created? One of the theories about it is that it was once the inside of a forming planet, because the planets that we know, Earth, Mars, Venus, Jupiter, have metal cores inside of them. So this may have been the metal core that was forming inside of a baby planet, which then collided with other planets that stripped off, forming planets that stripped off that rocky mantle, just leaving a piece of that core in space. And if that's the case, then by studying this body, we'll be able to study the cores of planets like our own, the Earth, in a way that we can never do otherwise.
Psyche is a larger asteroid in the main belt that is in between Mars and Jupiter. Our experience so far in terms of exploring the solar system has been with either rocky or icy bodies. What's particularly interesting about Psyche is we think it's a metallic object. We have a common understanding perhaps of how regular common rocks behave, but metal behave in a very different way. What I contribute to the mission is trying to understand how cratering and the process of collision and interaction work for a metallic object. And we will use this information then to understand what we see at the surface once we get there. What we did is take an iron meteorite, put it in the chamber and use it as a target for our input experiment. And we were shooting a quartz bead at high speed in order to produce a crater. Everything has been filmed with high-speed cameras, so we have a tremendous amount of data that shows in high resolution what happened during the contact, during the explosion, and how the crater forms on the surface. So everything has been documented in great detail. Here we have a piece of the Gibeon meteorite, and what we see here is a crater that was produced as a result of one of our experiments. And traditionally with rocks, the rim would be blasted away and would be a sort of flattish feature. But here we see these flaps that basically are frozen into place, and this is because the metal is much harder than rocks, and so you can then retain this interesting morphology. There's going to be a very exciting phase of the mission when we actually start gathering data, and there's going to be lots of surprises. I just can't wait to be there and see whether or not there is, any resemblance with this model or not.
There is nothing like the experience of sitting on console on launch day and hearing all the people go around and say, we're go for launch, and then finally getting to say yourself, we are go for launch. It's the culmination of all those years of effort and all those hundreds of people working, and so it's super exciting when you actually, finally say, we're go, and we're gonna get that beast into space. We're going to go launch and do a Mars gravity assist, go by this planet Mars, and then continue on to the asteroid using electric propulsion.
I think no matter what we think it is right now and how much we hypothesize what it might look like, I think it's going to really surprise us and change our views about our solar system when we get there. And that's it's an incredible opportunity to be a part of the team making that happen.
The Psyche mission has suffered several launch delays. However, it should be underway in the next year or two.
Three, 2, 1, 0. Liftoff. Atlas V takes flight.
Another ambitious mission that has launched is Lucy, to study several asteroid targets.
Tower clear.
So Lucy is going to survey 8 asteroids over a 12-year mission life. The first asteroid is in the main belt asteroids. It's Donald Johansen. And then the remaining asteroids are the ones that we call the Trojans. And because we believe that they are remnants of our solar system, by studying their geology, as well as their composition and their mass, then that will give us insight into planets, planet formations, and in particular the outer planets.
The Trojan asteroids, which are located in these Goldilocks zones of gravity-stable orbits in between the Sun and Jupiter, are really leftover fossils from the formation of the solar system. And these fossils are around 4 billion years old, and when the solar system was forming, they were brought into these locations. And the Trojan asteroids, which have been there since the formation of the solar system, are these last unexplored remnants from the cosmic neighborhood creation. And we're extremely excited to go and visit them because of our total lack of understanding of exactly what is out there. And so it's going to be extremely exciting when the Lucy spacecraft explores them.
Some of the most important planetary science questions we're trying to answer are focused on the origin and the evolution of the solar system. Asteroids and other small bodies are really important keys to understanding that history. Amazingly, many of these mysterious worlds have been altered very little in the 4.6 billion years since they first formed. Their relatively pristine state makes comets, asteroids, and some meteorites wonderful storytellers that have preserved clues they can share with us about conditions in the early solar system. In particular, by studying the Trojan asteroids, we can gain more insight into the history of the outer solar system and the giant planets, Jupiter, Saturn, Uranus, and Neptune. We actually find asteroids across the solar system, including near-Earth asteroids that are in orbits that periodically bring them close to Earth, main belt asteroids that orbit the Sun between Mars and Jupiter, the Trojans that Lucy will explore, and the Kuiper belt just beyond Pluto, which contains some of the most primitive objects in our solar system. Not all of these asteroids are the same, and Lucy is part of a collection of ambitious missions to study the diversity of these asteroid populations that will help us fill in more pieces of that cosmic puzzle.
Lucy will slingshot out from Earth's orbit and pass by the first target, a C-class or carbon-based asteroid named Donald Johanson after the famed archaeologist. Lucy will continue to the orbit of Jupiter and intercept 4 more targets: Eurybates, Orus, Lucas, and Polymele. Some are D and P class asteroids never seen before and theorized to be rich in volatiles and organics. The probe will then return to Earth for another gravity assist to the trailing Trojans of Jupiter, intercepting the twins Patroclus and Menetius, more P-class objects.
And Lucy spacecraft was named after the Lucy fossil because we will be studying asteroids, which are the fossils of planet formation. But the Lucy spacecraft and the Lucy fossil was named by archaeologist Donald Johanson and his team because apparently when they discovered the hominin, they were listening to the Beatles song Lucy in the Sky with Diamond. Now we do have a diamond. It's our beam splitter, which is on the LTES instrument, which is used to split the beam, is actually made of diamonds.
My job as a mission architect here at Lockheed Martin, it's very interesting, and it sort of encompasses the biggest picture of the mission. What is the trajectory? What sort of propulsion do you need to fly that trajectory? What does the spacecraft look like? So in the case of, for example, Lucy, it's like, okay, it's going out 5 times further from the sun than the Earth is. And so it's going to need big, huge solar arrays just because of that.
Lucy has 3 scientific instruments on board the spacecraft, and we'll also be using 2 of the spacecraft subsystems to contribute to the science investigation. With the LORRI instrument, we'll be able to get panchromatic images, which will tell us about the geology, and the crater history, which gives us the age of the surface. With the TESS instrument, we'll be able to measure the temperature of the surface at different points, and with the RALPH instrument, we'll be able to measure the composition of the surfaces. The Jupiter Trojans, they have a variety of surface characteristics. They have different colors and different surface compositions, and that leads us to believe that maybe they formed somewhere else.
After launch, the Lucy probe failed to lock one of its solar panels in place. Engineers are working on a resolution to this problem.
The Lucy spacecraft will travel 4 billion miles over its mission. And it is a very sophisticated, well-orchestrated trajectory that gets us there.
I cannot wait for those gorgeous images that our instruments are going to take and bring back to Earth. What that's going to tell me and the world is how gorgeous these objects are, what secrets they have to hold, and it's going to start us unlocking these mysteries of the solar system that are out there. I can't wait, and words can't describe just how excited I am to share with everyone these images when they first come back.
This animation is drawn from the recent data release of the ESA Gaia satellite. It reveals the locations of the larger asteroids within our solar system. This tapestry of orbits shows that several near-Earth objects cross our orbital plane. Geological history records that some have hit the Earth with devastating effects.
We've seen asteroids come through the atmosphere and kind of explode and cause some damage. And thankfully, so far, nothing recent enough that it really has a large impact on our civilization, but it could happen.
There are multiple different ways that you might attack the problem of, oh no, doomsday asteroid is inbound. One of those ways is a kinetic interceptor, which is what DART is working on.
As part of planetary defense, DART, which stands for Double Asteroid Redirection Test, its mission is to impact an asteroid in a binary system.
The reason we're doing this test is to try and prove out the technologies that would be needed to, say, save Earth if an asteroid were coming our direction and we needed to adjust its trajectory so that it would miss the planet.
SmartNav is the autonomous algorithm on board, and the purpose of SmartNav is to identify Dimorphos, which is the smaller of the two asteroids in the Didymos system, and we send maneuver commands to the spacecraft for the spacecraft to hit Dimorphos.
And we understand where about 40% of those asteroids are. We know that no known asteroid is a danger to the Earth right now, but the concern is about the asteroids we don't know about yet. And if we should ever discover an asteroid that's on a collision course with Earth, we want to be able to discover this years in advance so we can give the asteroid a push, not to destroy it, we probably wouldn't be able to do that anyway, but just to prevent that collision. And the DART mission, the Double Asteroid Redirection Test, is our first test of one way of doing that.
Launched aboard a SpaceX Falcon rocket, DART is well on its way to its target.
So the way an ion thruster works is that it utilizes electrical energy to ionize propellant and accelerate it using electric and magnetic fields. What NEXT does is that it increases the power level, you get more thrust out of it, it's more fuel efficient, it lasts longer, basically kind of improves things in almost every way and makes it very beneficial for end users to utilize.
When they're rolled out and fully deployed, they're almost 10 meters long. This is the last time that anyone will ever see these arrays fully deployed. Once we stow them here at DSS, they will not be deployed again until we're in space on the DART spacecraft. Part of our detailed inspection entails Andrew looking at the cell by cell on these arrays, again, that are almost 10 meters long. He'll look at them at different wavelengths of light, different angles, just to assure ourselves that we've found every anomaly possible in these cells and they're fully characterized with the entire array, and we know exactly what we have and the condition it's in when we launch.
DART's going to a binary asteroid, a double asteroid, for two really good reasons. The little asteroid, Dimorphos, which is in orbit around the big asteroid, Didymos, That asteroid is about the size of object that we would tend to be concerned about. The most abundant asteroids are the small ones, and this one, about 160 meters across, or about the size of a football stadium, is large enough that it really would cause severe damage if it struck the Earth. Now, by doing our experiment, a kinetic impact experiment on the small moonlet asteroid, we're able to measure our effectiveness in deflecting the asteroid by watching the change in the orbit of the little asteroid around the big one. It makes that measurement a lot more precise and a lot easier to do with telescopes on Earth. The other reason we're doing it is that the presence of the large asteroid there keeps the little one in orbit around it as the pair go around the sun. So that means that this asteroid, which is not a danger to Earth now, will never become a danger to the Earth because of anything that we do in the DART mission. DART is carrying a small CubeSat. It's called the Licia Cube. It was contributed by the Italian Space Agency, and its job basically is to watch the impact from a little distance away. It's riding along on the DART spacecraft, and it's going to be deployed a few days before the kinetic impact. It's going to maneuver and offset itself to the side so that it doesn't run into the same asteroid that DART is running into, and it's got 2 cameras on it that are going to try to first catch the actual impact of DART on camera, but then more importantly, see the ejecta, the plume of material that's blown off the surface of the asteroid and how that develops. If we're fortunate, we'll be able to see the impact crater newly formed by the DART impact. And then, of course, Licia Cube is going to do something that DART can't do, that is fly past the asteroid, look back, and get the full 3-dimensional shape of the object that we hit, which we won't know until we actually get there.
One other threat to Earth is the interstellar object passing through our solar system. They arrive without warning, fast-moving and having no known orbit. Another hazardous mountain in the dark. Orbit, a unique perspective on the planet. The permanently manned International Space Station circles overhead. It too gives us a unique perspective on science, health, and industry. The benefits of manufacturing in zero-G is spurring other countries and private companies to join this elite club of manned space stations. Low-cost, reusable manned spacecraft is the key to industrial expansion into space. SpaceX, with its Dragon spacecraft and Falcon rocket combination, is fulfilling that need. And other companies will follow.
It will become possible for people, I mean, of course, when I see all this, I've just yesterday seen the Dragon capsule right in front of me. We were able to get closer up to the same level. And I have to say, this is so fascinating. I really would like to step in and sit down and take off. It is a dream for many people.
This is what Dragon is.
Currently, the ISS is the only destination.
Space station and the forward.
The station is 23 years old and is reaching the limits of its ability to service other industrial needs. However, it is imperative to keep the research and science going.
because we do so much work on the space station, research, experiments that really help humanity, but also give us a different view of our planet. And at the end, we want to protect our planet, and our astronauts are really giving us messages back, which is quite unique and quite nice.
When we look at the science that's done on the space station, it's benefited us on Earth in a lot of different ways. And I think one is a very basic way, and that it's given the opportunity to scientists throughout the world to think about science in a different way. When we think about life as we know it, one fundamental property of all life has been gravity. And one of the first things scientists do is they think, what happens if we take gravity away? And on the International Space Station, we're allowed to do experiments that study just that for long periods of time. So we can study the effect of gravity on things, on people, and then sometimes we can combine that with the effects of radiation. We can also look at, when we think about future space missions, we know that it's going to take a while to get to Mars, and it's going to take some time to get farther. So the International Space Station has given us an opportunity to see what happens when humans are in a space environment or in a microgravity environment where they're in free fall for long periods of time. And this is really important, so we understand the effect of the lack of gravity on humans. We also understand what it's like to be confined in a small environment for long periods of time. And we're starting to understand just the kind of technology we need in order to create safe travel for humans, and also to address some of the challenges in robotic missions far from Earth.
The most recent addition to the ISS, a Russian segment with a European robotic arm, will help alleviate the stretched resources and capabilities of the station.
The ERA arm is completely symmetrical. This means it has a hand or an end effector at both sides, and that each side can serve as the tip as well as the shoulder. So it means that if you have multiple base points on the Russian segment, you can go from one base point to the other, then release your tip or your shoulder, which becomes tip, and then manipulate a payload. So in that sense, it has freedom of motion on the space station.
The robotic arm can be used for example, take payloads out of an airlock autonomously without the risk of an extravehicular activity, for example, and put equipment on the outside. It can be used for inspection. It can be used for putting big new modules, for example, and putting it on the space station, move big things around. And also it can be used to help the cosmonauts when they're doing a spacewalk, to move cosmonauts around or big payloads while the astronauts and cosmonauts have their hands free to work on the outside. So it can be used in several ways.
When we operate the ERA on the ISS, we're obviously going to learn a lot about how to use robots in space. How the robots work in space. We'll have feedback to our engineering process if we finally know what is the performance during its use in space. But we'll also learn on what we can best do with robots, what we can best do with people, and learn about the cooperation. And all of that is going to be very, very useful when we would go further into the universe and still have for sure robots initially, but maybe at some point in time also people with robots. So we're really looking forward to all what we can learn from the experience on the ISS with ERA.
Another addition to the station, delivered by a SpaceX cargo module, is a commercially funded Bishop airlock module. Operated by robotic arms, the commercial airlock allows easy transfer of payloads from within the station to outside for external deployment and to launch CubeSats, which is a burgeoning operational requirement. This will allow for more commercial payload throughput for industrial applications.
One issue that some European scientists worked on is that, first of all, we know that astronauts, after they've been in space for a long time, it's like their sense of taste changes a bit. And the longer they're up there, the more they crave spicier foods or saltier foods. So they start adding more salt to their meals. Well, one of the things that happens as they increase their salt ingestion is that it changes the pH of their blood. It makes it a little bit more acid, not a lot, but just a little bit. And so the body adapts to this acidity by trying to raise the pH just a little bit by providing calcium that comes from our bones. So they actually have increased dissolving of the bones to get that calcium to bring that pH up, but at the same time, we're also seeing that because they don't use their bones very much, because in a microgravity environment, you don't have to fight gravity to stand up straight, that they're already experiencing some bone loss. So we're starting to see that because of this, we're starting to see that this change of taste results in an increase in salt consumption that can actually speed the bone loss in space. So here we're seeing two different effects, and we know here on Earth, we now know that perhaps the salt, increased salt consumption isn't just a cardiovascular effect, but it could have perhaps contribute to bone loss and osteoporosis in humans here on Earth. And we didn't really see that effect until we went to space. The International Space Station provides a platform that we have humans that can act as subjects, but also operators of science. And it's also the only platform that we've had where scientists have the opportunity to do an experiment, see the results, and come back and prepare another experiment. And if something doesn't work, or if they have a second opportunity. And unfortunately, we don't see that with other missions.
What is next? We have now just a bit more than 20 years of ISS operation, very successful, and really incredible science and experiments that have been conducted, and we still learn every single day new things there, and this is really good. So what's next? What will happen is, for sure, that by the end of this decade, we will have commercial space stations up there. There are about 4 projects in the planning today in the US. And the question is, does Europe participate there? Does Europe have its own independent solution? And this is a big question that we need to address. But yes, the space station as we know it today, at the end of this decade, will not exist anymore and will be replaced by some commercial stations. And this is a big change. And Europe needs to be active and show leadership in making this change and really be part of it in this next era, which will come at the end of this decade.
2 commercial projects are well underway to develop commercial stations for industry and tourism. Axiom Space are developing their station to be assembled in 4 modules whilst attached to the ISS. The 4th module will allow the station to deploy its own solar panels and become independent from the ISS. Eventually, Axiom Station will detach and orbit independently from the ISS.
Hi, I'm Gerard Valle, and I'm the Structures, Mechanisms, and Soft Good Lead for Sierra Space Life Habitat. We're really just testing the structural restraint layer, which is what carries the load, and it's 1/3 the size of a life habitat.
So the restraint layer is made up of a material called Vectran. Vectran is an extremely high-strength material, performs really well in this application. It gets us the best performance while maximizing the livable volume inside the habitat.
Pretty amazing.
Sierra Space has been successful in developing their inflatable modules and are also developing their own spacecraft, the Dream Chaser, to service the station called Orbital Reef. First developed in test flight as a crewed reusable spaceplane in 2013, the Dream Chaser was not selected by NASA in their commercial crew program. However, Sierra Space persisted with an unmanned cargo version and have built 3 so far. The design of the lifting body was derived from an earlier cancelled NASA project, HL-20 spaceplane, a concept from earlier lifting body designs like the X-24 and HL-10. To be launched conventionally on a Vulcan Centaur or Ariane space rocket, and to fly back to Earth and land on a runway like the Space Shuttle. The craft will be powered with a vortex engine burning propane and nitrous oxide. It will be able to carry 5,000 kilograms of payload to the orbital reef, and eventually a crewed version will be capable of delivering between 3 to 7 crew or paying tourists. One growing problem, yet to be resolved for these new stations and other orbital assets, is space debris.
the moment, the most known encounters are between active satellites and space debris. An example of such an event happened in 2009, where we had a collision between an active telecommunications satellite, Iridium, with an inactive space debris satellite, Cosmos. So this collision actually resulted in thousands of fragments, and many of them are still in orbit.
The danger of space junk destroying operational satellites and even manned spacecraft is a growing concern.
Space debris is the result of our activities in space. So we have no longer functioning satellites, and we have spent upper stages and the fragments. And in total, we know of about 28,000 objects that we can track, that means follow up from ground. We know of 900,000 objects that are larger than a centimeter. And we know of about 128 million of objects larger than a millimeter. And that shows that the largest contribution in numbers are these small fragments. And unfortunately, collisions and explosions are forecast to continue in space, and that means the population will still grow.
We are launching more and more. In the past, it was only the big space nations, let me call it their way, that were launching. By now, space has been opened up to commercial activities, and therefore we see more and more satellites being launched. Is this an issue for space debris? I would like to say no, if people behave properly. So if we really manage in a proper way the end of life of the satellite, it's not going to be an issue. The point is, will we manage those satellites in a proper way, yes or no? And we see that there is a tendency still to disregard what do I do with my satellite once it reaches end of life, and not consider it since the very beginning. Situation has improved a lot in the past 10 years, but we still have to do some teaching on how important it is to be considered since the very beginning of the design of a project.
Several concepts are in play to remove this orbital debris. For the larger objects, capturing them with spacecraft with arms or grapples, then performing a deorbit burn, dragging the debris down to burn up in the atmosphere. There is another resource available in orbit: sunlight. Why not capture it with solar sails and beam the electricity down to Earth? Massive solar farms comprising of many small mass-produced solar satellites launched into orbit on low-cost reusable rockets. Assembled together in orbit using advanced robotic techniques, and once completed, these satellites will collect the full power of the sun's energy 24 hours a day, 7 days a week. and beam it wirelessly down to Earth to receiver stations, which will turn it back into electricity and deliver it to the grid. Space-based solar power, continuously available, inexhaustible, and sustainable. A scalable energy source that could help meet the world's clean energy goals. It is the closest planet to Earth in size and distance. It once may have had oceans and a similar climate. Now it is hostile and unforgiving. Scientists want to know why and how it changed. This could help with the hunt for other habitable worlds. For now, Venus could be considered Earth's evil twin. One of the brightest objects in the sky, Venus has been a world of mystery and conjecture. Probes were sent to briefly study the cloud tops as they passed by. The NASA Mariner mission, quickly followed by the Soviet Union's series of Venera flights. They left more questions than answers in their wakes. Eventually, Venera 4 landed a probe through the dense atmosphere onto a searing hot surface, followed up with more sophisticated probes that lived for a very short time. Other probes floated briefly in the dense, poisonous atmosphere. Mars became a much more attractive target, and Venus has been left little explored. In the late 80s, the Magellan probe was launched from the Space Shuttle. It mapped the planet's surface with radar, giving us a detailed look at the rugged surface of the planet. Stripping away the dense, thick atmosphere revealed intricate mountains, volcanoes, and lava fields, an uninviting and hazardous environment hot enough to melt lead. Following orbiters from both Europe and Japan also studied the surface features with radar. The Venus Express dipped into the upper atmosphere to aerobrake and descended into lower orbits. In recent years, several probes have used Venus for gravity assists to propel them to other destinations. Bepi Colombo, on its way to study Mercury, passed by, taking images and other readings. The maneuver, the second at Venus and the third of 9 flybys overall, helped steer the spacecraft on course for Mercury. Another European spacecraft, the Solar Orbiter, also utilized Venus for a slingshot as it closed in on its solar orbit. the Parker Solar Probe made a close flyby, taking measurements of the electric field of the planet and the radio emissions from the hot surface.
It's thrilling to be able to see something that's never been seen before. This emission that we're seeing is thermal emission. Even on the night side, the surface of Venus is so hot that it's glowing faintly at very red wavelengths.
These whisper images, I think, are really exciting because they provide a new window into the lower atmosphere and surface region of Venus where these extreme conditions exist.
A faint glow of heat from the night side shows distinctive features like continental regions, plains, and plateaus. A luminescent halo of oxygen in the atmosphere can also be seen surrounding the planet. These observations revealed much about the chemical composition of the surface.
Another really interesting thing we could look for is potentially mineralogical differences. Different rocks and different minerals emit different levels of heat.
Some surprising results suggested that water may have been on Venus in the past, but climatic changes and planetary processes removed the water from the planet and its atmosphere.
We have chemical fingerprints in Venus's atmosphere and on its surface, suggesting that Venus might have been habitable in the past.
The Wide Field Imager, or WISPR, is the sole imager aboard the Parker Solar Probe.
This is something that's truly new, and I believe will yield exciting science in the long term.
Once upon a time, Venus might just have been like an early Earth, with oceans, lakes, and rivers of liquid water, a much milder, oxygen-rich atmosphere. What changed the environment? Perhaps volcanic eruptions and toxic gases creating an atmosphere of carbon dioxide and sulfuric acid clouds, trapping heat in a greenhouse effect. Venus has the hottest surface of any planet in our solar system, hotter than Mercury. The atmospheric pressure is nearly 75 times greater than that of Earth. NASA and ESA are returning to the planet to find some answers. Europe is sending the spacecraft Envision, in partnership with NASA, which is providing the synthetic aperture radar system called VENSAR. The S-band radar will also act as a microwave radiometer and altimeter to map the surface. Envision will also carry 3 optical spectrometers designed to observe the surface and atmosphere of Venus, and a subsurface radar sounder that will probe the top kilometer of subsurface. NASA will also be sending Da Vinci and Veritas to Venus, due to be launched around 2029. Veritas stands for Venus Emissivity, Radio Science, INSAR, Topography and Spectroscopy mission. It will also map Venus's surface to determine the planet's geologic history. Germany and France are contributing to the infrared mapper and radar systems to determine whether active volcanoes are releasing water vapor into the atmosphere. Da Vinci, the atmospheric probe, will descend into the Venusian atmosphere to study the gases and chemistry with advanced sensors. It is designed to survive the descent to ground level whilst imaging its journey. The 1 meter wide probe will target a region called Alpha Regio, twice the size of Texas, and will add to scientists' understanding of rocky, atmosphere-bearing exoplanets that will be explored by new observatories such as the James Webb Space Telescope.
So Venus is cool. Venus is awesome. Venus is, in many ways, one of the most Earth-like planets that we know of. One of the key ways that it's different is that it's very, very dry. With temperatures on the surface of 460 degrees centigrade, and whatever that is in Fahrenheit, you would never expect there to be liquid oceans on the surface. That kind of temperature only boils off that water into steam, but the atmosphere of Venus is still incredibly dry, so where did the steam go? So to talk about how we remove something from a planet, we're going to have to talk about two forces of nature. Firstly, the force of gravity. Gravity is the thing which is holding you down to the planet, but if you think about it, it's also what is holding the atmosphere down onto the planet as well. If I want to remove some of the oxygen from the planet, we have to overcome that gravity. So to do that, I want to talk about the electric force. It's the thing which your device is using right now to pump electricity around its wires, right? It's pushing the electrons around the circuits. And what we think can happen is that the electric force can help push on the ions and in the upper parts of the atmosphere, push them off and up into space. So just as every planet has a gravity field, we think that every planet has a weak electric field. So we went looking for Venus's electric field, and boy oh boy did we find it. It turns out that Venus's electric field is at least 5 to 10 times stronger than at Earth. It's a monster of a force. It can rip heavy things like oxygen straight out of the upper atmosphere and send them kicking and screaming off into space. So this really changes the way we have to think about planets, because it turns out that planets can lose heavy things like oxygen to space entirely through electrical forces in their ionospheres. This is something that's really important if we want to go looking for exoplanets, for habitable planets around other stars. It is no good having conditions perfect for an ocean and an atmosphere that you might want to breathe if some invisible force is going to come along and rip it all off into space. Only understanding how atmospheres evolve can we try and understand how we got here.
Many orbiting telescopes and instruments are now in use to search for, identify and catalogue exoplanets, planets orbiting other stars. TESS, Kepler, Hubble, James Webb and the Nancy Roman telescopes are looking at planetary formations around various stars. Knowing how Venus evolved would give additional assistance to the planet searchers. This image is of a new star and its gas disk. The black rings show where planets are forming by gathering the dust and debris. This image reveals a moon forming around a gas giant as it evolves. This massive exoplanet orbits a white dwarf, the remnant of a dead star, and is slowly evaporating.
Another big unknown is to characterize planets that are orbiting other stars. So we could now, astronomers have got very good at finding these planets, but what we want to do is look at what they're made of. So what's in their atmospheres, or if they were rocky, what kinds of minerals are we seeing? And to be able to do that, I think will be stupendous.
So this, we can see the composition of the atmosphere in exoplanet, so what it's made of. And the specific planet we're looking at is hot. And so what we see in that is that there's water there. It wouldn't be in liquid form because the planet's hot, so it would be more like steam that's around it. But we can tell what's in that atmosphere.
So the James Webb Space Telescope is brilliant in a number of ways. One, it extends our wavelength all the way into the infrared, into the mid-infrared, so we can look for these heat signatures from these planets as well. But that also means we can cover the fingerprints of different materials in the atmosphere. So the Hubble Space Telescope looks for fingerprints of sodium and potassium and water in the atmospheres of these worlds. But the James Webb Space Telescope is going to be able to look for signatures of methane and carbon dioxide and carbon monoxide, as well as all of these wonderful water features that we'll be seeing in these giant planet atmospheres. But not only can it tell us in these different wavelength ranges, it's actually better resolution, so we can get more data points for each of these different molecules. And it's a much bigger telescope. We're collecting far more light. We can get a much better precision. So that means that the degree to which we believe our measurements is going to improve a lot with this telescope. And that's going to mean that we'll be able to tell you with confidence what we're measuring. Looking for life on other planets is the ultimate future goal of all of these missions, trying to understand how we got here, how the Earth is the way it is. The James Webb Space Telescope is taking us one step further towards that goal. We're going to be pushing to these smaller worlds where we can see what different planets that are unlike ones in our solar system are like, how atmospheres change with the size of your planet. And it's also going to give us information on these giant planets that we don't have in our solar system, so close to their star that they're hotter than a rocket. They're different worlds that we can explore with this, and every technique that we use with the James Webb Space Telescope is going to be the technique we need to be looking for life signatures on these other worlds. So getting good at using this technique is so important so that in the future we can be looking for these signatures.
So what we see here is what's called a hot Jupiter. So it's a planet that moves in front of its star, and it has about the size of Jupiter but the mass of Saturn. And what we see here is light filters through its atmosphere, and that allows us to look for the fingerprints of certain molecules. And in this case, the planet is full of water vapor, full of water. And that's what you see as wiggles in the spectrum. When we go and look at other exoplanets with Webb, we may look for other molecules, some that are familiar in our own atmosphere here as well, like carbon monoxide, carbon dioxide, or maybe even methane and ozone.
The total so far exceeds 5,000 exoplanets, with a further 8,000 to be confirmed. Of particular interest are the smaller, rocky, Earth-like planets.
We know our targets. They're bright stars which are known to host the type of planets we want to observe, and we will know when these planets transit. That is, when the planets move across the disk of the star, and we can measure the changes in the output of the star, the measured output of the star, in order to measure the size of the planet. will be focusing on smaller planets, so Earth-sized to Neptune-sized planets, which have been found by other missions, such as Kepler, to be very abundant around other sun-like stars, something which is not so much the case in our own solar system. So it's a big question. What are these smaller planets? What are they made of?
The range of planet types is amazing. Rocky worlds that sustain oceans and lakes, likely candidates for life. Others more extreme, like WASP 76P, tidally locked to its star, only ever showing one face to its sun. This extreme exoplanet has a day side where metals evaporate and a night side where it rains iron. Rogue planets that have no sun to orbit, ejected from their solar system and left to roam through space. Planets that have the heavy element barium in their atmosphere. Water worlds, planets still forming, others around dying stars. We must remember that amidst all these searches for a new Earth, we must take care of the one we have, because it is a very long way to travel to reach these other habitable worlds. Sea level rise is one of the most serious consequences of the human-induced climate crisis. The water rise is from heat expansion of the oceans, melting polar caps, vanishing glaciers, and the loss of fresh water. Satellites are an essential tool to monitor the changes and help climate modelers prepare us for the future. NOAA GOES-T satellite in geosynchronous orbit is a recent addition of the next generation of satellites. It is the Western Hemisphere's most sophisticated weather observing and environmental monitoring system, covering over half the globe. Along with the decades-long Sentinel series of satellites. Sentinel-6, a collaboration of European and US space agencies and climate monitoring institutes, is continuing the mission of uninterrupted, sophisticated data gathering for climate scientists and modelers.
Well, the main instruments on board include a dual-frequency radar altimeter. This is the primary instrument of the mission, and that's the one that's measuring sea surface height, significant wave height, and wind speed over the ocean. And from those measurements, we can actually have the superb measurements that we expect of sea level rise, but also the waves. The significant wave height, which is the top 1/3 of the waves, if you were to look at them in time, so the biggest waves that you would see. This is important for marine operations, and the altimeters provide perhaps some of the best data sets that we have today over the global ocean. We have plenty of buoys in the ocean that measure waves, but they're often in the coastal zone, and it's only when you go to the altimetry that you can really have this global coverage.
We all know sea level is rising. And how do we know that? Because we measured this since the 90s from space through a series of satellites. It started with Topex Poseidon, which was a French-American satellite, followed by the JASON 1, 2, and 3 series, which was also a French-American satellite. And Sentinel-6, as you said, also called JASON CS, stands for Continuity of Service, is meant to go in orbit to follow JASON 3 to continue the record of the sea level since about 30 years. And we want to continue that record for another 5 years and demonstrate and quantify the sea level rise we have been observing since the 90s. In average, about 3.2 millimeters per year, even though the scientists tells us in the last year this has been accelerating, in particular due to the acceleration in melting of ice. So over the last years, it's above 4 millimeters every year we record in the sea level.
We talk about the impact of melting snow and ice surfaces in terms of what's known as the albedo effect. When snow is dry, it's very reflective, and of course that helps to reflect sunlight back out into space, and the consequence is we can reduce the amount of melting this way. However, as ice and snow melt, the albedo and the reflectivity becomes lower, and this has the effect of absorbing more of the solar energy. This contributes to further warming and further melting. And so it's a runaway progressive effect caused by the reduction in the albedo.
Satellites are a major source of global, timely, long-term data sets, which is in particular very important for climate, because we need to have long-term data series to actually understand how the climate is changing over decades, for example, and to also understand what the trend of these changes are going to be. So we are using a large variety of different data sets. We're mainly concentrating on the European Space Agency's data sets, and there's a mixture between data sets that come from, a heritage mission, like for instance Envisat and ERS, because we're looking also back, of course, in terms of climate, but we're also using data that are coming in right now, for example, from the Sentinels missions that are running under the Copernicus program that we are running together or collaborating with the European Union and EUMETSAT together. But we're also using actually quite new technology and satellites that address scientific questions that haven't been addressed before. So it's a mixture of different data sources that we are trying to combine in these climate data records.
What we do is we also work with partner agencies worldwide. So we exchange data over climate. We do work on calibration activities. We support activities linked to, for example, ice loss volume monitoring, and we have done that with the US partners over INVIE campaign over the Arctic region.
To calibrate the satellites in orbit, scientists on the ground take measurements in situ all around the globe, from the Antarctic to the Arctic and glaciers around the world. They then compare results and validate the satellite data.
And we're producing climate data records, so long-term data records of climate-relevant indicators, let's say. One of them you see behind me. We are also producing climate data records for glaciers, in particular the extent of the glacier, the velocity, but also the elevation.
The ice loss in the Alps is comparably strong. So we have similar strong mass loss, I think, in the Andes of Peru and Bolivia, but also in Patagonia. They have similar rates. But the most difficult thing or problematic thing is that this ice loss in the Alps is still increasing. So now I think for something like 30-35 years we see higher and higher loss. And this takes place despite the fact that the region where ice can melt, the so-called ablation region, is shrinking. And this is a very strong signal for accelerated climate change and an increased forcing, which means that temperatures have to increase and push the snowline higher and higher so that more areas are exposed to melt.
Those projections tell us what glaciers will look like. What they will look like very much depends on what we, human beings, will do next in terms of greenhouse gas emissions. So if we manage to mitigate climate change very much, we will have glaciers that will still shrink, but will shrink a lot less than if we don't manage to get hold of this climate crisis that is literally unfolding. So in the worst case, where really our emissions will continue to go unabated until the end of the century, well, this place where we're standing is going to be ice-free for sure. But even the highest elevation that we see here, they'll most likely be ice-free as well. On the contrary, if we now really manage to put effort in abating emissions, we'll be able to save, say, at least 40% of the ice. So half of this place is gone anyway, but still there will be something that we can look at and that we can show to our children and that our children can show to our grandchildren.
I think the recent record since Cryosat, one of our satellites, has been flying, has shown that there's quite some fluctuation in the amount of ice transferred from land to the ocean. However, we have seen that sea level rise has been accelerating over the last several years. One of the reasons is thought to be related to the increased melting of land glaciers. And a recent publication has shown that in fact the contribution of glaciers to sea level rise is increasing. And we've gone from a situation in the 1970s and 80s where it was contributing only a fraction of a millimeter a year to something closer to 1 millimeter a year. This is around 20-25% of the sea level rise signal globally. And so glaciers are obviously having an increasing contribution to sea level rise over the last 2 decades.
The European Space Agency is doing a lot in providing the evidence for a changing climate. If you think about the Earth observation program, for example, I think the majority of activities are really directly addressing this question, and it starts at the perceiving new satellite measurements. So one of the core activities of the European Space Agency in the Earth observation program is, of course, to build satellites, and there's different flavors of these satellites that address new technologies, new scientific questions, like for instance the Earth Explorers. But then there is the Sentinel missions that we are developing in collaboration with the European Union and with EUMETSAT, who provide, for example, continuity on many of these measurements, but also improve over coming decades, because we have a lot of experience in these measurements. And I think so we're doing in ESA, I think something, it's almost like covering the entire food chain of providing climate relevant information, and I think this is quite an amazing fact, because we really follow through from the beginning of the measurement up to the point where we're actually talking to the people who put the policies in place, and I think that's a really good foundation that we're providing from the ESA's perspective.
So when you fly around the Earth at 400 kilometers, you have a very unique point of view that is at the same time a privilege and a curse. It is a privilege because, of course, not many people get to do it. Not many people get to fly in space and look down at the Earth. It is a curse because what you see is, at the same time, so beautiful and so fragile that it certainly breaks your heart. And it is what inspired me to start talking about what happened, what is happening on planet Earth, and about everything that we take for granted today. And as a matter of fact, that same feeling of helplessness and desire to do something, I felt in these last couple of days, talking to the scientists, talking to the explorers, and being myself part of the group on this glacier and looking with my eyes, touching with my hands, the same things that I felt from space. So if I had to summarize the feelings, which is always hard because feelings don't come in a linear way, they're always very mixed up. I feel a little bit of urgency. And because it's me, I also feel hope that people will listen and understand the urgency of what is happening and how fast we have to react before everything that we have will disappear.
Low-lying regions of the world, of course, are going to suffer the most from this kind of impact in terms of ice melt and sea level rise. Of course, countries like Bangladesh already suffering from the increased probability of storm surges as sea level rises, and coastal inundation is a problem for millions of people in Bangladesh. We also see it in more developed countries. We have a situation in Venice during seasons of the year where tidal range and storm surges combine with sea level rise to cause what's known as aqua alta. And there, the whole of the city of Venice is inundated by water on a regular basis during these periods of time. So I think the societal impact of coastal inundation and flooding can affect millions of people in the future. And so we need to monitor the effects of melting ice and sea level rise.
We got the long-term data. And we got the long-term trend, and we now finally realize that you have the long-term trend, but you also have superimposed local variations. So some years it stops, and other years it goes very quick. So it's a really very dynamic system, and that just really means that we have to have a continuous monitoring from space.
I believe that there is an awareness that is growing, but is not enough yet. So water being probably one of the resources that we really need to check, and we are here because of that. Water as a cycle that we have interfered with. Ice turns into water, turns into atmospheric water, and it accelerates hurricanes, it accelerates flooding, it's all connected, and we have interfered with that cycle. So now we have to do something to take a step back. Well, one of the things that we can do is preservation without pollution. So little steps that everybody can do. Have a bottle of water and reuse it instead of continuing buying extra new bottles of water and polluting the earth with the plastic and using extra water that we don't need. We can live on very little water. We are just not used to do it because we don't think about it, and we take it for granted. I believe that the perspective that I have comes from the awareness that on the space station we live on very limited resources. We have to recycle them, and we have to respect that awareness.
What we're doing in the Climate Office, and not just in the Climate Office, but in the European Space Agency Earth Observation Program at large, is, I think, 99% supporting the cause of understanding what our climate is doing, how our climate is changing, and that in turn can actually inform policymakers to take action of what needs to be done to either mitigate that effect, so basically, for example, limit emissions, or to adapt to things that we cannot change anymore. It's a very important physical evidence to give decision makers and policymakers a base to come up with plans of how we address this issue.
Ice is changing a lot and ice is melting a lot. Whether it's a problem, of course, long term it's a problem because the sea level rise will go up. But it's also to some degree an opportunity for some of the Arctic countries that they can develop their countries. So it's climate change, monitor what is happening, make sure we can give a qualified statement, and especially the space is very important to give a qualified statement of what is really happening and not just some model prediction or some fancy outlook which could be way off. So I think we're the guys who give the hardcore facts. And as you say, I've been here for many years. I've seen the change on my own eyes because before we even got involved with the European Space Agency, we did a lot of airborne, a lot of mapping work. We mapped with the first satellites already in the very late 1970s as the very first users of satellite navigation, namely for mapping remote and distant areas. So it's been really amazing to see, and also amazing to see the changes, and the changes are big, no doubt about that.
And we're producing these data sets also for the benefit of addressing these international climate drivers, so that we actually know where we're standing at the moment in terms of the state of the climate and what actions need to be taken in the future in terms of policy and decision making and adaptation and mitigation actions, for example, in the future.
Because of the availability of information that we are constantly bombarded with, there is a general feeling that we can all be experts at everything and come up with our own opinion. I don't want to dismiss anybody's opinion, but I do want to listen to what experts and people who have devoted their lives to a certain study have to say. Now, it's a cycle. We have scientists who use their instruments to gather data, study those data, and come out with a theory. And once they come out with a theory and everybody agrees to it, then we should probably listen to that. But how do they get these instruments? How do they gather that data? Well, there is a whole community of people, technicians, engineers, astronauts, operators, that work constantly, incessantly, to create the instruments and to position them and to create the basis so that the data can be collected in the correct way.
The sea level will go up, no doubt about that. So people in Holland and the very low-lying areas, they should have good reasons to be concerned. So do we in Denmark. But again, right now it's only 10 centimeters, so we're talking 2,100, we talk anywhere between 30, 40 centimeter and a meter, then it's a little bit more concerning. And again, that's where this long-term space mission, they will tell these people who make the modeling and the prediction in the future, if they made the modeling earlier, will it really fit what we see today? If you take all the data today, will it fit in 10 years? That's why you have the big value of these continuous data. And also the continuous measurements really of, do the satellites measure the right thing? Is the radar really measuring the surface, or is it measuring somewhere else on the ice? That's all the questions we are concerned with.
Most scientists agree we are past the point of no return. Now the focus is on trying to mitigate the most serious effects on the planet.
So it is a concern, of course, and eventually we should do something about it. And again, the space mission can tell you in the long run, if you change something in the CO2 with the political side, will it really matter? And for instance, the CO2, also in the Copernicus program and the ESA missions, you have CO2 missions, which are really useful to actually pinpoint who are the bad guys in this game, who is not cutting back eventually.
As a scientist, I think we can provide data, and the satellite data help us to do so. The issue with the glaciers and the shrinking glaciers is a global scale phenomenon where people are really concerned that in the future there is no more ice or much less ice. And what we can provide as scientists is solid data about how much ice there is, how the ice masses change, and maybe when you do some computer modeling, also how much ice there will be in the future. And over the past 20, 30 years, I think the reporting from us was more and more, yes, they are shrinking, and glaciers are shrinking globally, and they do it stronger and stronger. And we can repeat this information again and again and have it in IPCC reports and say, hey, there's a problem. But of course, in the end, it depends if this message is picked up and converted to action. And here is then very soon the place where the engagement of scientists end, because this is a political thing, and what we can do is provide the best data and the best uncertainty information we can get, and say, really, we are sure about this and about this and about this, and not so sure about this. And then politicians have to decide on if they want to do something about it. And we hope that at some point this will happen.
Artemis, the sister of Apollo. She will soon be returning humans to the moon. The decades of development are nearly complete. New hardware, new ways of making the journey, and new goals have been set. This time, the United States will not be going it alone. This time, it's an international effort. The first major test will be Artemis 1, an uncrewed journey to the moon and beyond, a final hardware shakedown for manned flights.
Nowadays, astronauts, engineers, and scientists are very excited to go to the moon because it's pure exploration. It's discovering terra incognita. We would go to regions that were never been, well, explored by a human, neither robotically nor in person. The moon is really our 8th continent, and it's there to be discovered. Last time humans have been there was in the 60s and 70s, and they covered, 12 people covered 6 landing sites, and imagine that in an area that's so huge. It really doesn't give us a lot of knowledge about the moon itself.
2, 1.
This lunar spacecraft comprises ESA's ESM and NASA's Orion crew capsule. It will be used for an uncrewed certification flight, performing a 6-day orbit around the moon.
We returned to the moon for various reasons, different technologies, and it is a big achievement, I believe.
All over in Europe, we have companies in 10 countries helping to put this ESM together, which is quite significant. And actually, there are hundreds and thousands of people working within Airbus, but also in our partner companies, to make this endeavor a successful mission.
Monitoring of the performance of the ESA segment will be conducted here at ESTEC in the Netherlands.
And that one is only on one side.
These folks here are specifically taking care of the European Service Module, which provides the human capsule part of that with all of its power and life support. So this team here is really taking care of the crew that'll be going to the moon and beyond.
I mean,
So there are mainly 2 types of support. That's basically 2 types of situation. Nominal situation, everything goes fine. Here we are actively supporting, actively monitoring the spacecraft, looking at the trend of the parameters to try to predict as much as we can if something is, if a failure is building up or if everything is nominal. And again, anticipation is the key, meaning that you have to know your mission and you have to know what's coming up, what's coming next, for instance, if it's, and then things you cannot predict, and that's why we are training with failures in the simulations. These are failures. And to failures, how we react, how we talk on the voice loops, how we communicate throughout the position between the various subsystems to quickly identify what is the failures, to investigate it, to understand the root cause, and also any likely impact onto the other subsystems, on the system, and also on the mission.
That's human spaceflight, and you're always going to have anomalies. We don't say a problem. A problem is indicative of something you don't know that, but anomalies come from in engineering. You can find them, solve them, and continue on. And that's what the teams have been working through recently through the wet dress rehearsals. There was 4 dress rehearsals to make sure everything's absolutely right.
Anyway, you can do like this. Yeah, you can. If you click shift.
Today's simulation is what they call an inspection simulation. So the idea is during a launch, they will do a systematic inspection of the entire spacecraft. The European Service Module sits on top of the NASA SLS rocket. So basically, on a pre-launch check, they'll just really systematically look at every piece of those vehicles, trying to identify any potential anomalies or such before they fly.
The surface of the moon has about the same area as Africa, and we only visited the moon 6 times in the 1960s and 1970s. So if you think about landing in 6 different spots in Africa, you quickly realize that there's so much more left to learn and understand about how the moon formed and how it's evolved over the last 4.5 billion years.
Before NASA's Artemis astronauts go to the moon, a small spacecraft called Capstone is leading the way. This small spacecraft will test a unique lunar orbit that has never been flown before. This orbit will be home for NASA's Gateway elements.
Behind me is a mock-up of the Habitat and Logistics Outpost, or as we call it, the HALO module. The HALO module and the power and propulsion element will be delivered to lunar orbit to make up the first components of NASA's Gateway. The Gateway is going to be crew-tended, where crews will visit the Gateway for a period of a few weeks or a few months. HALO and the PPE are just the first components of the Gateway, with plenty of room for future growth. Northrop Grumman has been delivering cargo to the International Space Station using the Cygnus spacecraft since 2013. That's 15 missions and counting. We are now using that Cygnus experience and our lessons learned in the design of the HALO module.
With the power and HALO modules in place, the Gateway will be built up over several launches. The IHAB module will be delivered by the first manned Orion mission. A logistics module with the Canadian robotic arm will be next. The lunar landing system, then Artemis 3, will deliver the refueling infrastructure and telecommunications module before proceeding on to a landing at the lunar southern pole. Before any descent attempt, a crucial component for Artemis is location of a landing site. Unlike the Apollo missions that landed along the relatively flat equatorial regions, Artemis will be landing at the southern pole of the Moon, a far more challenging landing scenario. Six landing regions have been identified, close to the permanently shadow regions where water may be found. However, further exploration of these sites is required to pinpoint the most ideal landing location. This will require the services of robots. NASA is sending Viper to scout the terrain.
Viper is a rover of many firsts. First NASA rover to map water resources, and it's the first rover to wear a headlight.
Viper will be one of many robots descending on the lunar pole in search of water. Testing these robots is well underway in terrain most lunar-like.
Traditionally, rovers are operated from the Earth. With the lunar gateway being put in place around the Moon, there's the possibility of controlling them directly with much smaller time delay. And this opens up for new possibilities for things that you simply cannot do or is much more difficult to do from the Earth. So now we're here in Sicily. We're repeating our experiments on the slopes of Mount Etna. The astronaut is not on the International Space Station. He's controlling from a hotel room here. We have our European Space Operations Center in Germany, in Darmstadt, who are directly overseeing and running the operations. And in the role play, they are pretending to be on the Moon, and it's very realistic because the slopes of Mount Etna is a wonderful lunar analog. It looks exactly like the Moon. There's beautiful craters, there's rocks, it's grey. So we have the European Space Operations Centre able to really immerse themselves in the role play, feel like they are planning traverses and exploring regions of interest on the moon, in close discussion with the scientists who also get this full immersion where they see a realistic lunar-like geology, so they can have a real discussion. They need to then communicate this to the European Space Operations Centre, who has to then make decisions about how they are going to execute operations, whether they make use of the astronaut for direct teleoperation with a short time delay, or whether they make use of their own tools for planning longer traverses and not wasting astronaut time on this. So this is the type of trade-offs and the sort of things that we want to learn how to do for real when we go to the moon, by playing essentially the scenario, playing the game here on Mount Etna. The astronaut is doing the same as he did on the International Space Station in 2019. So he has a control station which allows him to fully teleoperate the rover. What I mean by that is that he can drive it, he can control the arms with the direct feedback. So we have a very immersive control station which allows him to feel a bit like he's on the surface. The robot is his avatar on the surface. It's designed so that he can touch things with the robotic arm and feel what the robotic arm feels. It's designed so that he can decide whether he wants to drive with the joystick, or he can plan his traverses and automatically do it. He can choose whether he wants to manually pick up rocks, whether he can do it automatically. And we really want to learn from his experience which of these tools he is using, which of these tools he is finding useful in different situations, and how his interactions are happening with the science team, how easy it is to communicate which samples to pick up, how the interactions are going with the European Space Operations Centre, when they think it's better that he uses his tools to do it, or when it's better that they do it, how the handovers are working. All of these things is what we're trying to learn here. It's a very complex experiment because it has a lot of stakeholders, a lot of partners, because there's a lot of different objectives. We are trying to validate technologies that have not really been used extensively in space. We have this device we used in 2019. It's the first time something like at this level of complexity has been used to control robots from the space station. We have the whole operational scenario, which involves a lot of parties, this game, which is we're trying to learn a lot from. So this complexity makes it a very challenging experiment, but that way we learn a lot.
We are here at Mount Etna in the frame of the Artemis campaign, and this campaign is organized by the German Aerospace Center. So there are multiple robots from the German Aerospace Center, via guests, our robot from ESA, and also other research institutes are actually practicing with their robots how it is on a real scenario. So here on Mount Etna, it is very close to what we expect on the moon in sense of soil conditions and harsh environment, dusty, rocky slopes and loose sand. Our robot is controlled today by an astronaut. For this purpose we invited Thomas Reiter. And for us it's important that's an astronaut, because in these scenarios we want to practice what happens in reality. So there would be an astronaut sitting in the spacecraft and controlling a robot on the surface of a planet. And in the past we have done this with the ISS. So we had Luca Parmitano in 2019 with Analog 1, controlling our robot in a hangar in Falkenberg. And here, of course, we are on Mount Etna, moon-like scenario, but it's very difficult to have an astronaut on the ISS controlling a robot here on the mountain, to have all the logistics and everything set up at the same time. But to have a fair comparison, we indeed have Thomas Reiter in the hotel room in Catania, controlling a robot here in a realistic scenario.
Yeah, today was a very special scenario because we tested the cooperation between a ground control, people who are sitting in a control room somewhere on Earth, and the crew that is orbiting around the moon in the lunar gateway. And this specific cooperation turned out to be extremely fruitful. In earlier times, it was always thought that there is either a purely robotic operation, which is exclusively controlled from control centers on the Earth, and the crew doing something in situ, being really on the surface of the moon. And I think what we learn here is that this kind of collaboration that you are doing from ground control on the Earth, a crew that is on board a space station that is orbiting the moon, and a rover that is on the surface, can be extremely efficient and much more efficient than actually if either one does it alone.
Well, it's certainly less dangerous to send a rover to the surface than to send an astronaut. It's also cheaper. It's also possible to not take up so much of their time. You know, astronaut time is extremely valuable, so you can send a rover to the surface. You can let the ground team do all their planning, let them do all the longer traverses, and you get the astronaut involved when it's necessary for maybe the more complex task or the things where he really direct teleoperation, direct control of the robot is more helpful.
Our rover is built by the lab and it's a demonstration rover. So we want indeed to figure out what features do we need in a future space mission. So of course, if you control a rover, you need for awareness video cameras for the simple ones. But of course, to go somewhere, you need a locomotion platform, and it needs to be fitted for this loose soil underground. And to manipulate things, for example, pick up rocks or maybe later maintenance of infrastructure, you need robotic arms. And so our robot was constructed with this purpose in mind, to have it controlled by an astronaut with force feedback to perform this kind of tasks. But of course, we are also looking in the future, so direct teleoperation is good. But of course, we also want to enhance our system by more and more autonomous features. And so there, my team developed, for example, automated rock detection, so that the astronaut doesn't need to grasp the rock manually, but indeed that the machine learning algorithm detects a rock, controls the robot to grasp it automatically. And this way, we want to step-by-step increase the capabilities to automated driving, automatic obstacle detection, rock detection, to come actually from a remote operated system to a more autonomous system. Today we try to achieve a full control and a full scenario of our robot. So in the past experiments we went always step by step. So we had a force feedback device on the station, we had a robot in a controlled environment, and indeed this is one of the first times we put out the robot in a really harsh environment here on Mount Etna. So it's moon-like, we have a complex scenario with the operations center in the background, the astronaut with time delay in the control center, and indeed a task that has been prepared by the team in Darmstadt that was not known to the scientists and to the astronaut beforehand. So here we really try to get as close as possible to real scenarios with surprises in a hard environment. And if we master this, we are really confident that these technologies can be developed further to make it space grade, to indeed be part of the next moon mission.
In our scenario, which is based on a notional mission, based on the European Large Logistic Lander, the astronaut, in collaboration with the European Space Operations Centre, would be collecting the samples, bringing them back to the lander, and then they would be brought back to the gateway or directly to Earth for analysis by the scientists.
Autonomous robotics will be used not just on the moon, but farther afield. Plans are underway with the Mars Sample Return mission. Landers and launchers are being developed for this mission that will see an autonomous robot, or even perhaps helicopters, that will land on Mars and pick up the samples collected by the Mars rover. Once brought back to the lander, they will be loaded onto a launcher, returned to orbit, collected by the orbiting vehicle, and carried back to Earth via a small re-entry vehicle holding the precious cargo. Two advanced space probes are now orbiting the Sun, one from NASA, the other from Europe. They have begun studying our star up close, imaging the mechanisms of hot plasma and magnetic fields, even diving into its atmosphere, discovering new insights into the solar winds and the science of the stars. This is the Royal Observatory of Belgium in Brussels. Scientists have been studying the Sun from here for over 100 years, using telescopes like this. The observatory is also the World Data Center for the Sunspot Index. It is now receiving data from the European Solar Orbiter, a wealth of information studying the Sun up close, well within the orbit of the planet Mercury. The imagery alone is spectacular, giving us a whole new perspective of our Sun and the nearest star.
It sometimes happens, I get into my office, I download the latest data and I stare for hours at it. It's so addictive actually. Nobody has ever seen the details of the corona in that much detail before. So every time we get an image down, it's the first time we see something at that scale, and that's really fascinating. It's really discovery space that we're entering.
I was personally blown away by the quality and degree of detail in these images. And clearly, as solar physicists, we've been looking at images of the Sun for many years. But by going 3 times closer, we can get the spatial resolution up by a factor of 3. And we see things that we haven't seen before. And that's, of course, the beauty of science, to explore the unexplored.
The journey of Solar Orbiter began in 2020 and has traveled over 2.5 billion kilometers, with gravity assists from Venus and Earth.
The spacecraft is performing very well, and we are very happy about that, because it is the first time that it had to go so close to the Sun, and so in this very challenging environment. And of course the spacecraft is designed for it, but this design is all based on modeling, on predictions, so you only really know that it's going to work until you have seen it working.
Solar Orbiter is basically a research mission, but ultimately we want to be able to predict space weather. These are energetic events that could have an impact on high-tech installations on Earth, GPS satellites, power grids. And we want to make sure that in the future we can predict geomagnetic storms based on solar activity. And for that we really need to take the Sun's temperature and measure the solar wind and connect the two. By going close to the Sun, we try to capture the physics of space weather events, and we want to film on the Sun the events that give rise to changes in the near-Earth environment. And we need to fly close to the Sun to be able to measure the solar wind while it's still in a pristine, undisturbed state.
One of the great mysteries of the Sun is the difference in temperature from its surface to its atmosphere, where it increases by 1 million degrees in a process that is not yet understood. Generation of the high-speed solar winds emanating from the star is another process under scrutiny.
For the mission, it's important in many ways, because on one hand, of course, the closer you go, the better resolution you get and the more details you can see. And it's also important because we want to understand the influence of the Sun on planets, on the Earth. And for that we want to come closer and we want to see what's happening and at the same time feel around the spacecraft how the environment is changing.
So the EUI, so the Extreme Ultraviolet Imager, sees the hot corona, so to speak the atmosphere of the Sun, at extremely high resolution, much higher than what we had before. And one of the problems that we are after is to understand why the corona is so hot. It's like 1 million degrees or so, while the surface of the Sun is 5,000, something like this. And that's really puzzling, and we're after that since decades. And we think that it's possibly because of tiny eruptions that go on all the time, but that are small, too small to be seen by other instruments. And now that with Orbiter we get so close to the Sun, we can finally see them. And we did see a lot of them in the first images that we took. And the closer we get, the more we see. So we are really excited about this because we may finally be on the solution to that decade-long problem.
These measurements that the spacecraft is taken now and also later will be important to improve our understanding of the Sun. One of the things we want to understand better is how the Sun affects the Earth, but for that you have to really understand how the activity of the Sun is caused, how it evolves, and when, for example, such a cloud of solar material leaves the Sun, how it also propagates through space and goes towards the Earth. So for that we want to do several of those close passages to the Sun to observe it from close by, and we also want to change the orbit of the spacecraft so that it can see the solar poles, because we have never ever seen those before, and they are important to understand the magnetic field of the Sun.
The Solar Orbiter carries 10 instruments on board. Imagers of various frequency, including an X-ray spectrometer and extreme ultraviolet imager, a magnetometer energetic particle detector, and a solar wind analyzer suite. It also carries a radio and plasma wave suite, which measures electric and magnetic fields around the spacecraft.
So now the whole payload is working together. It's actually a lot of work to coordinate all that. But what that gives us is that we get a comprehensive diagnostics of the of the solar plasma, of the solar atmosphere. So we can, with EUI, get the dynamics, the fine-scale structure, but then with other instruments like SPHEREx, we can get measurements of the temperature, of the density, these kind of things. So with all the instruments together, we get a comprehensive view and understanding of the physics. And then you have all the in-situ instruments also that we are working with that will help us understand what the coronal mass ejections are and how they influence the physics of the heliosphere, which is the surroundings of the sun, so to speak.
By having all 10 instruments on Solar Orbiter operate together, we can really harness the entire power of this mission, which is designed to connect remote sensing observations of the sun, meaning pictures and spectra, and what you measure, essentially feeling the solar wind as it flies past the spacecraft. And for that we need all 10 instruments, and they've now all been tested and exercised and tuned like musical instruments. And so this is the first time we actually got all 10 working together as a team.
So this solar orbiter and the instruments on it, it's a new machine that we are bringing to a place in the space that has never been visited before. So when we do that, we cannot expect everything to work as it is designed or is expected. There is a steep learning curve to learn to operate the thing, and that's what we call commissioning phase. And we're now at the end of that phase, and we have learned how to operate our machine to the best of its capacities, and the results are actually fabulous.
It's important to have all the instruments working and operating in a coordinated way, because one of the main goals of the mission is to link the sun and its activity with the environment, and not only the environment close by, but also the planets. And for that we want to look at the sun's activity, at the solar activity, with many different telescopes that look at it in different wavelengths. So that means they are looking at different layers in the atmosphere, and they can also measure things like the magnetic field on the sun. And then at the same time, we also have instruments at the outside of the spacecraft that will sense and measure what's happening around the spacecraft itself. So whenever there is solar activity, we can feel the effects close to the spacecraft.
Among the things that we now see for the first time are really tiny sources of energy release in the corona. And we are now very curious to find out in what sense they are connected to the large-scale structure of the solar wind and the energy that gets essentially put into the flow of particles towards Earth. And we try to really use models to connect what we see on the surface to what we see in the wind. And that is something that clearly takes more time and investigation to really pinpoint where a solar wind package came from. But we believe that we've done quite well in terms of pointing at the right place, and thereby we hope to get this complete picture of cause and effect. Close approach of solar orbiter to the sun, to about a third of the distance between sun and Earth, is so important because it allows us to get measurements of the solar wind in an almost pristine state before it gets mixed on its way to Earth. And more importantly, to combine these measurements with pictures of the sun and spectra that we can then connect and get a complete picture of the sun and solar wind.
Scientists are also studying the dangerous solar storms that affect Earth.
This first perihelion was clearly our first scientific milestone after getting all the instruments calibrated. So this really gives us good confidence that we'll be able to do this again, and we'll do it roughly twice a year when we fly by the sun again. In between we'll be far away from Earth, so that takes a lot of time to get the data downloaded. But in between these far away periods, we have also close by periods where we can dump all the data that we've accumulated, and then it's Christmas for the scientists to look at the data and get new scientific insights.
The Parker Solar Probe is the second spacecraft now operating close to the Sun. It was launched by NASA in 2018 and has taken 4 years and several gravity assists to reach its operational orbit. Its elliptical orbit, bringing it closer and closer to the star's corona, a boundary layer not clearly understood. This project has been over 50 years in the making.
The fact that the sun is hot has been a major technological challenge and why it's taken us so long to fly Parker Solar Probe.
That design of the heat shield, where the front of the heat shield that faces the sun is hot enough to melt aluminum, but the backside, where the spacecraft electronics and instruments are, is actually at room temperature. That's been the key to getting this mission done.
This is a dream come true. One of the major goals for the Parker Solar Probe mission is to fly through the solar corona, and we are doing that now.
The edge of the sun's atmosphere is known as the Alphen critical surface, a postulated zone where the solar wind goes from a slow to extremely fast speed, spreading out through the solar system. The Parker Solar Probe has passed through this barrier into the corona, showing that the boundary is indeed lumpy and has sampled material still bound to the sun.
Two of the most challenging scientific mysteries in astrophysics occur in a region that we call solar corona.
The instruments on board have shown that outside the boundary, the solar winds accelerate away from the sun at high speed, unable to fall back onto the surface. However, inside the boundary, the magnetic field is much stronger, and solar material is much slower, tied to the surface.
That we've always known that the atmosphere of the sun, the corona, spins with the sun, spins at the same speed that the sun does. But out at the Earth, the solar wind is moving straight out from the sun, so it's no longer spinning. Where that transition happens is very important for understanding, because that spinning of the corona actually helps slow down the sun. All stars get slower in their spinning as they get older. Parker Solar Probe sees that transition from spinning to straight happens further from the sun than we thought. And that actually has implications for every star in the universe and how they slow down. And that's important actually for the habitability of solar systems around distant stars.
Gaining knowledge of our sun will help us understand all the other stars around us. This will help us with the search for habitable exoplanets. Understanding the processes of the solar winds and energetic particles will assist with finding worlds that, like the Earth, have magnetic shielding to help protect living organisms on the planet's surface.
Parker Solar Probe is the first mission to get close enough to the sun to see where the action is actually happening, where the solar wind is accelerated, where the corona is getting heated. And we've seen a lot of new science that we don't completely understand, but there have been some remarkable results about small events that we can see in Parker Solar Probe that get smeared out in the 93 million miles between the Earth and the sun.
We are so excited for these new results coming down from Parker Solar Probe. Parker has gone closer to the sun than we've ever gone before. It's inside the orbit of Mercury. We're seeing the solar atmosphere as it emits its material out into the solar system. We call that the solar wind. And we're seeing this process up close and personal at a higher detail and complexity than we've ever seen before.
actually as it's being formed. So we're able to study the solar wind and all of its variability and complexity up close like we just can't do from Earth.
The protective magnetic field surrounding Earth is constantly buffered by solar winds and energetic particles. At the poles, these solar disturbances create spectacular auroras. It may also cause the atmosphere to leak out into space.
So the sun not only has this constant solar wind that blows out in all directions, it has solar storms, solar flares, and coronal mass ejections. And those energetic storms can accelerate particles up to almost the speed of light. And those energetic particles can actually cause radiation sickness in astronauts if they're out unprotected when those happen. On the Earth, we're protected by the Earth's magnetic field and the atmosphere of the Earth. But once you're out in space, away from the Earth's magnetic field, those can be a danger to not only astronauts, but also spacecraft.
The sun is capable of energizing pieces of atoms up to really high speeds and energies, and these are damaging to astronauts and to electronics. Now, we're protected down here on Earth from these particles, but on the moon or beyond, astronauts wouldn't have that luxury. So one of the key missions of Parker Solar Probe is to understand how these particles are actually being accelerated so that we can better predict and protect against them.
Another phenomenon of our sun deals with space dust and debris, pieces that clump together by static electricity, and then as they grow by gravity, there appears to be none close to the sun.
Space dust is pieces of comets and asteroid debris that fills our solar system, but close to the sun, they can be so hot that they actually vaporize, or that material can also be pushed away by the radiation of the sun. And so there ought to be a region around the sun where there is no dust. And for the first time, Parker Solar Probe is seeing evidence of this dust-free zone.
So the sun goes from a quiet period, what we call solar minimum, to solar maximum, and back again, about every 11 years. And we launched into a very quiet solar minimum. That's actually helping this mission because during solar minimum, things are simple. There aren't very many sunspots. There aren't very many of these solar storms. What ones we're seeing are small, and that allows us to individually identify every single event.
And then later, as Parker continues to observe the sun, we'll see this ramp up of activity and energy bursts, and we'll be able to see the more complex and bigger energy bursts.
In the coming years, the probes will witness up close the power of the sun during its more active phase, as it spirals closer and faster to the star.
Parker Solar Probe is already the fastest human-made object. As it gets closer to the sun and spirals in and goes faster and faster, it will reach 500,000 miles an hour. So we are so excited to see the results as Parker continues on its mission.
Before Parker Solar Probe passed through the sun's Alphen boundary, it detected kinks in the solar wind, where it would momentarily double back on itself. Scientists call them solar wind switchbacks, but had no idea of the mechanism that caused them to form. As Parker got closer and closer to the sun, it detected more and more of these switchbacks. It was able to track one of them to its origin on the visible surface of the sun. On the surface, you can see defined cells as heat rose from beneath. These convection cells churned and created funnels of magnetic energy above the surface. Scientists concluded that these switchbacks form inside these funnels before rising into the corona and beyond. This is only one piece of the puzzle. However, scientists still don't yet know how they form. Over the next few years, Parker will keep looking for clues as it explores our sun up close. The sun is the only star we can study like this. It is also the only star we know that supports life on at least one of its orbiting planets. Understanding it is critical as we search for life beyond our solar system.
That will link directly into the question, are we alone in this universe? And that is one of the biggest questions for humanity to answer.